Deep in the constellation Leo, 124 light-years from Earth, the James Webb Space Telescope has captured something that will change everything we thought we knew about life in the universe. A world where the temperature holds steady, where the atmosphere pulses with chemistry that should not exist, where molecules hang in the air that on Earth are produced only by living things. Scientists are calling it K2-18b. A planet 8 times more massive than our own, wrapped in hydrogen and floating in a global ocean that may stretch hundreds of kilometers deep. The data is not speculation, it is measurement. The Webb telescope has detected dimethyl sulfide in the atmosphere of this distant world, a molecule so rare, so chemically unstable, that on our planet it exists for only a few hours before breaking apart. Yet there it is, concentrated thousands of times stronger than anything we see in Earth's skies. Replenished, sustained, breathing into space. On Earth, only one thing makes dimethyl sulfide: life. Specifically, the microscopic organisms that drift through our oceans. Phytoplankton exhaling sulfur as they metabolize, bacteria processing organic matter in the soil. The faint scent of a sea breeze carries traces of it. Without biology, it simply does not form. The telescope's instruments have reached what scientists call 3 sigma confidence, a 99.7% certainty that the signal is real, less than 3 chances in 1,000 that this is error or noise, the same statistical threshold used to discover subatomic particles, the same standard that confirmed gravitational waves. This is not a hint, it is evidence. The implications are staggering. If this molecule exists where the data suggests, then we are not alone. Somewhere beneath crimson clouds and endless waves, chemistry has become biology. Metabolism has written itself into an alien sky. A world we will never touch has already touched us with the light it sent a century ago. But K2-18b is not just alive. It may be more habitable than Earth itself. Its temperature never swings, its oceans never freeze. Its parent star will burn for trillions of years while ours fades in mere billions. This is not a planet clinging to existence in the margins of possibility. This is a world built for endurance, and if one exists, how many others are out there breathing quietly in the dark? Prepare yourselves, we begin. The numbers arrived on a quiet morning in December 2023, hidden within streams of infrared light that had travelled for over a century across interstellar space. At Cambridge University's Institute of Astronomy, Niku Madhusudan sat before his screen, watching the faint dips and rises of spectral data. Each curve was a clue, each wavelength a whispered secret from a world he would never see. The James Webb Space Telescope had been watching K2-18b for months. Every 33 days, the planet crossed in front of its star, blocking a fraction of light. During those transits, starlight filtered through the planet's atmosphere, and molecules in that air absorbed specific wavelengths, leaving fingerprints. Madhusudan's team had captured dozens of these transits, building a composite picture of what hung in that distant sky. First came water vapour, expected, logical, then methane and carbon dioxide. Both consistent with a hydrogen-rich atmosphere surrounding a world with liquid water. The data fit the profile of what astronomers call a Hycean world, a planet with a global ocean beneath a thick hydrogen envelope, somewhere between a rocky Earth and a gaseous Neptune, a new category of habitable environment that theory predicted but observation had never confirmed. Then came the anomaly, a single spectral feature that should not exist. A dip in the infrared signal at a wavelength corresponding to dimethyl sulfide. Madhusudan stared at the line, checked the calibration, ran the analysis again. The signal remained, faint but persistent, concentrated at levels thousands of times stronger than anything seen on Earth. On our planet, dimethyl sulfide exists in concentrations below 1 part per billion. It forms when phytoplankton metabolize sulfur compounds in the ocean, releasing the gas into the atmosphere. Within hours, sunlight breaks it apart. It is constantly produced and constantly destroyed, maintaining a delicate equilibrium that depends entirely on the continuous activity of living organisms. But on K2-18b, the telescope detected concentrations exceeding 10 parts per million, a staggering abundance. If the signal was real, something was producing this molecule at rates far exceeding anything biological processes generate on Earth. And because dimethyl sulfide degrades so quickly, whatever was making it had to be making it continuously, right now, as the light travelled toward Earth. As Madhusudan examined the data, the implications settled over him slowly. This was not a geological signature, not a chemical artifact of a dead world's atmosphere. Every known abiotic process that could produce dimethyl sulfide required conditions that did not exist on K2-18b. High concentrations of hydrogen sulfide that the telescope had not detected. Low concentrations of carbon dioxide contrary to the abundant CO2 already confirmed. The data refused to fit any lifeless scenario. Madhusudan called his colleague Subhajit Sarkar. Together they ran the numbers through independent analysis pipelines. Different algorithms, different assumptions. The signal persisted. They checked for contamination from Earth's atmosphere. None. They looked for instrumental artifacts. Found nothing. They calculated the probability of random noise producing such a feature. Less than 3 in 1,000. The discovery had been made using Webb's NIRISS and NIRSPEC instruments, capturing near-infrared wavelengths as the planet transited its star. But near-infrared observations alone were not enough. To confirm the finding, they would need to observe K2-18b in a different wavelength range using a completely independent instrument. They proposed additional observations using MIRI, the mid-infrared instrument, which would see the planet's atmosphere in wavelengths, where dimethyl sulfide absorbs light differently. Months later, the MIRI data arrived. The same spectral signature appeared. Independent wavelengths, independent instrument. The same molecule announcing itself from 124 light-years away. The team also detected another related compound, dimethyl disulfide, from the same chemical family. Both molecules overlapped in their spectral features, making it difficult to determine which was more abundant. But both pointed toward the same conclusion. Something on K2-18b was exhaling sulfur into space. Madhusudan knew the weight of what they were claiming. Extraordinary claims require extraordinary evidence. The phrase echoed through every astrobiology conference, every peer review, every public statement about the search for life beyond Earth. They were not claiming to have found life. They were claiming to have found a molecule that on Earth is produced exclusively by life, present in concentrations that suggested ongoing biological activity. The statistical significance stood at 3 sigma. In particle physics or gravitational wave astronomy, that level of confidence marks a strong detection worth publishing. But it falls short of the 5 sigma threshold required for claiming a definitive discovery. 5 sigma means a probability of less than 1 in 3.5 million that the signal occurred by chance. 3 sigma means roughly 1 in 370, compelling, but not yet conclusive. The team calculated that between 16 and 24 additional hours of observation time with Webb could push the detection to 5 sigma. They submitted the proposal. But even without reaching that threshold, the data represented something profound. For the first time in human history, astronomers had measured a potential biosignature in the atmosphere of a planet orbiting another star in the habitable zone. The news spread quickly through the astronomical community. Some researchers expressed cautious excitement, others voiced skepticism. Questions emerged about whether unknown photochemical reactions in a hydrogen-rich atmosphere could produce dimethyl sulfide without biology. Laboratory experiments on Earth had shown that under certain conditions, sulfur compounds could form through purely chemical processes. But those experiments required ingredients that Webb had not detected on K2-18b. Madhusudan remained measured in his statements. He emphasized that while a Haitian world teeming with life was the scenario that best fit all the data, they could not yet rule out unknown abiotic mechanisms. Science advances through falsification, not confirmation. The goal was not to prove life existed, but to test whether the hypothesis could survive scrutiny. Yet beneath the careful language, a quiet certainty grew. The data was real. The molecule was there. And if it was there for the reasons the evidence suggested, then humanity had crossed a threshold. The question was no longer whether life exists elsewhere. The question was how to be certain, how to look at light from 124 years ago and know with absolute confidence that something alive had exhaled into the darkness. Madhusudan thought about the photons that had reached Webb's mirrors. Each one had left K2-18b in the year 1901, when Earth was just beginning to send its own signals into space. Radio waves, the first wireless transmissions. While those early broadcasts were spreading outward from our planet, light was already travelling toward us, carrying the chemical signature of another world's breath. Now, over a century later, those photons had arrived, and they were telling a story that demanded to be heard. K2-18b does not resemble Earth. It is not a twin of our world, not a mirror image floating in a distant solar system. It is something stranger and potentially more remarkable. A planet that exists in a category we're only beginning to understand. The numbers tell part of the story. K2-18b has 8.6 times the mass of Earth. Its radius stretches 2.6 times wider. If you could stand on its surface, assuming a surface exists beneath the crushing depths, gravity would pull at you with roughly twice the force you feel now. Your weight would double, your movements would slow. But the planet's size and mass place it in an ambiguous zone between rocky worlds and gas giants. Too large to be Earth-like, too small to be Neptune. For decades, astronomers categorized planets into simple groups. Terrestrial worlds like Earth and Mars with solid surfaces and thin atmospheres. Gas giants like Jupiter and Saturn with no true surface at all, just layers of hydrogen compressing deeper into liquid and metallic states. But as telescope technology improved and exoplanet discoveries multiplied, a new category emerged: planets between 1 and 4 Earth radii, sub-Neptunes and super-Earths, worlds that have no analogue in our solar system. K2-18b sits near the boundary, large enough to have accumulated a massive hydrogen atmosphere during its formation, small enough that it may still possess a liquid water ocean beneath that atmosphere. This combination, if real, defines what Madhusudan and his colleagues call a Haitian world. Hydrogen plus ocean. A planet where a rocky or icy core is wrapped in a deep ocean, which is in turn enveloped by a thick hydrogen-rich atmosphere. The concept challenges assumptions about habitability. For years, the search for life beyond Earth focused on finding planets like ours. rocky worlds orbiting sun-like stars at distances where liquid water could exist on the surface. The Goldilocks zone, not too hot, not too cold. Earth became the template, but templates limit imagination. Hycean worlds offer something different. Their thick hydrogen atmospheres act as thermal blankets, trapping heat and distributing it evenly across the planet. This means the habitable zone around their parent stars extends much farther than it would for a rocky world. A planet that would be too cold for liquid water on Earth-like worlds might maintain a comfortable ocean temperature beneath the hydrogen envelope. K2 18b receives roughly the same amount of stellar radiation as Earth. Its distance from its star places it in what astronomers call the habitable zone, the region where temperatures allow liquid water to exist. But unlike Earth, where water pools on the surface exposed to space, K2 18b's ocean would exist beneath kilometers of dense atmosphere, protected, insulated, stable. The atmosphere itself tells a story. Webb's observations detected water vapor, methane and carbon dioxide, each present in concentrations around 1%. The hydrogen that dominates the atmosphere is nearly transparent to the telescope's infrared instruments. But the trace gases absorb specific wavelengths, creating the spectral fingerprints that reveal their presence. Water vapor was expected. Any planet in the habitable zone with a hydrogen atmosphere would likely have some water mixed in. But the presence of methane and carbon dioxide together creates an interesting chemical environment. On Earth, these gases exist in a delicate balance maintained by biological and geological processes. Methane is constantly produced by microbes and constantly destroyed by reactions with oxygen. Carbon dioxide cycles through photosynthesis, respiration, and weathering of rocks. On K2 18b, without oxygen, the chemistry follows different rules. Methane and carbon dioxide can coexist more stably, but their presence in roughly equal proportions suggests active processes rather than dead equilibrium. Something is producing these gases. Something is consuming them. The atmosphere is not static. It breathes. Temperature measurements indicate that K2-18b maintains a surface temperature around 49 degrees Celsius, roughly 120 degrees Fahrenheit. Warm by Earth standards, too hot for humans without technology. But within the range where many extremophile organisms on Earth thrive. Thermophilic bacteria live in hot springs at similar temperatures. Deep-sea hydrothermal vents support entire ecosystems in water exceeding 100 degrees Celsius. More importantly, the temperature appears stable. K2-18b orbits its star every 33 days, close enough that tidal forces likely lock one hemisphere in permanent daylight, the other in permanent darkness. But the thick atmosphere circulates heat efficiently. Models suggest temperature variations across the planet remain minimal. No freezing nights, no scorching days, just steady, persistent warmth. This stability may be K2-18b's greatest advantage over Earth. Our planet experiences wild temperature swings, day and night, summer and winter, ice ages and greenhouse periods. Life on Earth evolved to survive disruption, to adapt to change, to endure catastrophe. But what if life could evolve without disruption? What if chemistry had time and stability to explore every possible configuration? The ocean beneath K2-18b's atmosphere would be unlike anything on Earth. Hundreds of kilometers deep, perhaps deeper than our deepest ocean trenches by orders of magnitude. Pressure would increase with depth until water reached supercritical states, no longer clearly liquid or gas, but something in between. Near the core, if a rocky core exists, pressure would crush carbon into diamond. Water would become ice not through cold, but through compression. Yet in the upper layers, where pressure remains manageable and temperature holds steady, conditions might be remarkably hospitable. The hydrogen atmosphere dissolves into the ocean, creating a unique chemical environment. Water mixed with hydrogen forms a lighter, less dense fluid than pure water. Buoyancy changes, chemistry shifts. Reactions that would be impossible in Earth's oceans become possible. Think of K2-18b not as a planet but as a laboratory. A cosmic experiment in what happens when you give chemistry time, stability, and unusual conditions. The hydrogen-rich atmosphere provides both insulation and reducing chemistry. The deep ocean provides pressure gradients and layers where different processes can occur simultaneously. The steady stellar input provides energy without the violent swings that characterize Earth's climate. If life emerged there, it would not resemble life here. No photosynthesis powered by visible light. No oxygen metabolism. No solid ground on which to build structures. But chemistry does not need Earth's template. It needs gradients. Energy flowing from hot to cold, from high concentration to low. Given gradients and time, chemistry explores every available pathway. The detection of dimethyl sulfide suggests that at least one of those pathways has led somewhere remarkable. On Earth, this molecule forms through specific biological processes. Marine phytoplankton convert dimethyl sulfonionate, a compound they use to regulate osmotic pressure, into dimethyl sulfide as a byproduct. The sulfide escapes into the atmosphere. Within hours, photochemical reactions break it apart. But on K2-18b, dimethyl sulfide concentrations measure thousands of times higher than on Earth. Either unknown abiotic processes are generating it at prodigious rates, or biological activity far exceeds the productivity of Earth's oceans. The molecule does not persist by accident. It persists because something keeps making it. What that something might be remains speculation. But the planet itself, its size, its atmosphere, its ocean, its stability, creates conditions where the question becomes not whether life could exist, but whether anything could prevent it. Chemistry tends toward complexity. Given energy and time, simple molecules become complex. Complex molecules interact. Interactions become patterns. Patterns become metabolism. K2-18b has had time, billions of years. Its parent star formed long before our Sun. The planet has orbited in relative stability, while Earth experienced mass extinctions, ice ages, asteroid impacts. If chemistry began to organize itself into something recognizable as life, that life has had opportunity to refine itself beyond anything evolution produced here, this is not a planet at the edge of habitability, clinging to existence in marginal conditions. This is a world built for endurance, a planet where the question is not whether life could survive, but what life could become given unlimited time to experiment. The star at the center of this story burns with the light our eyes would barely recognize. K2-18 is a red dwarf, a classum star with less than half the mass of our Sun, small enough to fit inside Jupiter, dim enough that from Earth's distance it would provide no more illumination than a full moon. Yet this apparent weakness conceals the star's greatest strength. Patience. Red dwarfs are the tortoises of the cosmic race. They burn hydrogen so slowly, so efficiently, that their lifespans stretch beyond human comprehension. Our Sun will exhaust its fuel in roughly 10 billion years total. It has already consumed half that time. In 5 billion years it will swell into a red giant, incinerating Mercury and Venus, boiling Earth's oceans into space. Life on our planet has an expiration date written in stellar physics. K2-18 will still be shining when the Milky Way has changed shape, when galaxies we see today have merged or drifted beyond the cosmic horizon. Red dwarfs can live for 10 trillion years. Some estimates push even higher. They are the longest-lived stellar objects in the universe, burning with such miserly efficiency that their fuel supply seems nearly infinite by any timescale that matters to biology. This longevity transforms what habitability means. On Earth, complex life took 4 billion years to emerge. Single-celled organisms appeared relatively quickly, within the first billion years after the planet cooled enough to support liquid water. But the jump from simple cells to complex multicellular life took another 3 billion years. Evolution is not fast. It explores slowly, testing configurations, most of which fail. Around K2-18, that clock never runs out. If microbial life emerged on K2-18b a billion years after the planet formed, it would have already had more time to evolve than life has existed on Earth, and it would have trillions of years still ahead. Time enough for chemistry to become biology. Time enough for biology to become something we have no words for. The star's spectral output concentrates in the infrared. Red and near-infrared wavelengths rather than the visible light that drives photosynthesis on Earth. This means any organisms on K2-18b that harvest stellar energy would need different pigments than chlorophyll. Plants on Earth appear green because they reflect green light while absorbing red and blue. Plants around a red dwarf would likely appear black or deep purple, absorbing every available photon from the narrow band of usable wavelengths. But photosynthesis may not be the dominant energy source on K2-18b at all. The thick atmosphere and deep ocean mean that little starlight penetrates to depth. Instead, chemical energy may drive the biosphere. On Earth, hydrothermal vents in the deep oceans support ecosystems that never see sunlight. Chemosynthetic bacteria convert hydrogen sulfide and methane into organic compounds, forming the base of a food web that includes tube worms, crabs, and fish. K2-18b's ocean, if it exists, would be warmer and more chemically active than Earth's deep sea. Dissolved hydrogen from the atmosphere provides a rich source of reducing power. Dissolved carbon dioxide offers building material for organic molecules. At the interface between the hot interior and the cooler upper ocean, chemical gradients would be steep and sustained, perfect conditions for metabolism to begin and persist. The star's stability matters as much as its longevity. Red dwarfs in their youth are violent. They flare frequently, hurling radiation and charged particles at their planets. But K2-18 is old enough to have calmed. Observations show no signs of excessive flare activity. The radiation environment appears benign, or at least no more hazardous than what early Earth experienced. K2-18b orbits close to its star, completing a year in just 33 days. This proximity would be deadly around a Sun-like star, but around a red dwarf it places the planet squarely in the habitable zone. The reduced stellar output means that to receive Earth-equivalent radiation, a planet must orbit much closer. K2-18b sits at roughly 7 million kilometers from its star, about 1/20th the distance between Earth and the Sun. This close orbit likely locks the planet tidally. One hemisphere forever facing the star, one hemisphere forever in darkness. On a rocky planet with a thin atmosphere, this would create extremes. The day side would bake, the night side would freeze. But K2-18b's thick hydrogen envelope circulates heat efficiently. Winds at high altitude carry warmth from day to night, distributing energy across the entire globe. The result is not a planet of extremes, but a planet of equilibrium. Imagine standing on the day side, if standing were possible. The star would hang motionless in the sky, neither rising nor setting. Its light would cast the landscape in permanent deep red twilight. Shadows would stretch forever, unmoving. The horizon would blur into haze where atmosphere meets ocean or ocean meets atmosphere, boundaries becoming uncertain in the thick air. On the night side, darkness would not be absolute. The atmosphere itself would glow faintly from residual heat. Auroras might shimmer as charged particles from the star interact with the planet's magnetic field. Lightning could flicker in storm systems powered by the temperature differential between day and night hemispheres, and above it all, the stars would shine with a clarity impossible on Earth, undimmed by artificial lights or scattered by thin air. The Terminator, the band of permanent twilight between day and night, might be the most habitable region. Here the star hovers perpetually on the horizon. Temperature remains moderate. Light is sufficient for vision but not overwhelming. If K2-18b has a solid surface, if islands or continents rise above the global ocean, this twilight band would be prime territory for complex life. But more likely, K2-18b has no continents, no islands, just ocean from pole to pole and atmosphere above. In such a world, the vertical dimension matters more than horizontal geography. Life would stratify by depth. Surface organisms, if any exist, would drift with currents under clouds that never fully part. Mid-depth life would inhabit the zone where pressure and temperature balance perfectly. Deep life would cluster near the warm boundary with the planet's interior. Each layer would develop its own chemistry, its own energy sources, its own evolutionary pressures. The result would not be a single biosphere, but a stack of interconnected ecosystems, each producing waste that becomes food for the layer below, each processing energy and matter in cycles that span the entire depth of the ocean. The star's gift to K2-18b is not just longevity, but constancy. No seasons, no climate shifts, no ice ages or greenhouse periods. The stellar output remains steady within narrow bounds. The planet's orbit does not precess significantly. The atmosphere does not escape to space. Everything that begins has time to continue. On Earth, extinction events reset the evolutionary clock. Asteroid impacts, volcanic super-eruptions, ice ages that lock the continents and glaciers. Life recovers, but each recovery means starting over, rebuilding diversity from whatever survived. K2-18b, orbiting its quiet red sun, may never have experienced such catastrophes. Evolution there would be cumulative, building complexity without interruption. This raises a question that astronomy cannot yet answer. If life has had billions of years to evolve in stable conditions on K2-18b, how complex has it become? Are we detecting the chemical signature of simple microbes, or of something that has progressed far beyond the bacterial stage? The dimethyl sulfide in the atmosphere could be the metabolic waste of phytoplankton analogues. Or it could be the industrial byproduct of something that builds, communicates, thinks. We have no way to know, not yet. The telescope sees molecules, not organisms. It measures concentrations, not consciousness. But the star's eternal light implies that whatever exists on K2-18b has had every opportunity that time can provide. And time, more than any other resource, is what evolution requires to work its transformations. The James Webb Space Telescope does not orbit Earth. It floats 1 million miles away at a gravitational balance point called L2, where the combined pull of Earth and Sun creates a stable pocket in space. Here, in perpetual darkness, shielded from the warmth of both our planet and our star, Webb maintains a temperature colder than the surface of Pluto. This cold is not accidental. It is essential. Webb sees in infrared. The universe glows with heat that our eyes cannot detect. Planets warmed by their stars, dust clouds heated by newborn suns, distant galaxies whose light has been stretched across billions of years of cosmic expansion. To detect these faint infrared signals, Webb itself must be cold. Any warmth from the telescope's own structure would overwhelm the delicate photons it is trying to capture, like trying to see stars while standing next to a bonfire. The telescope's sun shield accomplishes this cooling. 5 layers of material, each thinner than a human hair, stretched across a frame the size of a tennis court. Each layer reflects heat back toward the sun. Between the layers, vacuum provides insulation. The result is a temperature gradient from 85 degrees Celsius on the sun-facing side to minus 233 degrees Celsius on the side that watches the cosmos. This 318-degree difference creates an environment where Webb's instruments can operate at the edge of physical possibility. 18 hexagonal mirrors, each coated in gold thinner than a human cell, combine to form Webb's primary mirror. Gold reflects infrared light with near-perfect efficiency. The mirrors are not fixed in position. Tiny motors adjust their alignment constantly, compensating for the minute thermal expansions and contractions caused by the telescope's own faint heat. Together, these mirrors collect light with such precision they could detect the thermal signature of a bumblebee on the moon. But detecting K2-18b requires more than sensitivity. It requires timing and geometry. The planet orbits its star in a plane that, by chance, aligns with our line of sight. Every 33 days, K2-18b passes directly between its star and Earth. These transits last for hours. During that time, a fraction of the star's light passes through the planet's atmosphere before reaching us. Molecules in that atmosphere absorb specific wavelengths. Each molecule has a unique signature, determined by how its atoms vibrate and rotate when struck by photons. Water vapor absorbs certain infrared wavelengths. Methane absorbs others. Carbon dioxide has its own pattern. Dimethyl sulfide leaves its mark in yet another spectral region. By measuring which wavelengths diminish during transit and comparing them to the star's normal spectrum, astronomers can identify what gases exist in the planet's air. The challenge is in the numbers. K2-18b blocks roughly 0.1% of its star's light during transit. The additional dimming caused by atmospheric absorption is a tiny fraction of that already tiny signal. We are measuring changes of perhaps 1 part in 10,000. At a distance of 124 light-years, through Earth's own atmosphere, which must be accounted for and subtracted. With instruments pushed to their operational limits, Webb accomplishes this through multiple observations using different instruments. The first detection of dimethyl sulfide came from data collected by NIRISS, the Near-Infrared Imager and Slitless Spectrograph, and NIRSpec, the Near-Infrared Spectrograph. These instruments observe in wavelengths between 0.6 and 5.3 microns, capturing the region where many molecules have strong absorption features, but a single observation is never enough. Confirmation requires independent evidence. The team proposed using MIRI, Webb's mid-infrared instrument, which observes at longer wavelengths between 5 and 28 microns. Different wavelengths mean different molecular vibrations. If dimethyl sulfide is truly present, its signature should appear in both spectral regions, though the exact pattern would differ based on which molecular motions are being excited by photons of different energies. The MIRI observations confirmed what NIRISS and NIRSpec suggested. the spectral features attributed to dimethyl sulfide appeared in the predicted wavelengths. Moreover, the data showed evidence of dimethyl disulfide, a related molecule from the same chemical family. Both compounds absorb infrared light in overlapping regions, making it difficult to determine their individual concentrations precisely. But their combined signal strengthened the case that sulfur-based organic molecules exist in K2-18b's atmosphere. Each transit observation adds to the statistical confidence. The more times Webb watches K2-18b cross its star, the more precisely it can measure the atmospheric composition. Random noise averages out over multiple observations. Systematic errors become identifiable when the same measurement yields consistent results. The current detection stands at 3 sigma significance. Additional observations could push it to 5 sigma, the threshold generally accepted for claiming a definitive discovery. Webb's instruments can also measure how the atmospheric signal changes with altitude. Different layers of the atmosphere have different temperatures and pressures, affecting which molecules can exist and at what concentrations. By analysing the precise shape of spectral features, astronomers can infer the vertical structure of the atmosphere, estimating where clouds form, where hazes condense, where chemical reactions are most active. The telescope cannot see the planet directly. K2-18b is far too faint, its light drowned out by the star it orbits. But indirect detection through transit spectroscopy reveals more than a direct image ever could. An image would show a dot of light. Spectroscopy shows composition, temperature, pressure, chemistry. It transforms a dot into a world. Consider what each photon represents. Light leaves K2-18's surface, travelling outward in all directions. A tiny fraction encounters K2-18b's atmosphere. Most passes through unaffected, but some photons strike molecules of water, methane, carbon dioxide, dimethyl sulfide. These interactions steal energy from the photons, shifting their wavelengths slightly, or absorbing them entirely. The modified light continues toward Earth. 124 years later, a few of these photons arrive at L2. They strike Webb's gold mirrors, focusing down through the telescope's optical system. They enter one of Webb's instruments, where they are sorted by wavelength using diffraction gratings or prisms. They strike detectors cooled to within degrees of absolute zero, generating tiny electrical signals. These signals are digitized, transmitted to Earth, processed through algorithms, and finally transformed into the spectral graphs that scientists analyze. Each photon is a messenger. It carries information encoded in the precise quantum state it acquired when it interacted with molecules 124 years ago. That information survives the journey intact, waiting for instruments sensitive enough to read it. Webb reads those messages with extraordinary precision, measuring not just which wavelengths are present, but their exact intensities, their variations, their relationships to one another. The telescope has observed dozens of exoplanet atmospheres since beginning operations in 2022. Each one teaches astronomers something about how to interpret the data. Which spectral features indicate clouds, which suggest hazes, which arise from molecules and which from instrumental artifacts. K2-18b is not the first planet Webb has characterized, but it is the first where the spectral signature points so clearly toward a potential biosignature. Future observations will refine the measurements. Webb will continue monitoring K2-18b through multiple transits, accumulating data that can distinguish between dimethyl sulfide and dimethyl disulfide with greater certainty. It will search for other molecules that might accompany biological activity. It will measure seasonal variations, if any exist on a tidally locked world. It will map how the atmosphere changes between the day and night hemispheres, but Webb cannot answer every question. The telescope observes in infrared, perfect for detecting molecular absorption but limited in other ways. It cannot determine whether the ocean is global or patchy. It cannot measure wind speeds directly. It cannot see beneath the clouds to whatever surface might exist below. Other telescopes, future missions, will fill these gaps. For now, Webb has done what it was designed to do. It has captured light from another world and decoded the story written in that light. The story speaks of chemistry and stability, of molecules that should not persist without ongoing production, of an atmosphere behaving in ways that on Earth are associated exclusively with life. The story is incomplete, but it is compelling, and it is real, measured in photons that travelled for over a century to deliver their message to instruments built to receive it. Temperature is not just a number. It is the pace at which chemistry happens, the speed at which molecules vibrate, the rate at which energy flows from one state to another. Too cold and reactions slow to nothing. Too hot, and the delicate bonds holding complex molecules together break apart. Life exists in the narrow band where chemistry is fast enough to be interesting but slow enough to be stable. On Earth, temperature swings wildly. Day and night can differ by 30 degrees Celsius. Summer and winter by 50 or more in temperate regions. Ice ages lock continents in glaciers for tens of thousands of years, then release them into relative warmth. Organisms must adapt to survive these fluctuations, developing dormancy mechanisms, migration patterns, insulation strategies. Energy that could go toward growth and complexity instead goes toward merely surviving the temperature roller coaster. K2 18b does not have this problem. The planet maintains a surface temperature near 49 degrees Celsius, approximately 120 degrees Fahrenheit. This measurement comes from analysing the thermal emission spectrum, the infrared light the planet itself radiates based on its heat. The temperature stays constant, no seasons, no dramatic day-night swings despite tidal locking, no ice ages, just steady, persistent warmth. This stability emerges from the planet's thick hydrogen atmosphere. Hydrogen is the lightest gas, the most efficient at redistributing heat. On Earth, nitrogen and oxygen dominate our air, and they do transport heat through convection. But hydrogen, being less dense, circulates more readily. Wind patterns on K2-18b likely move heat from the day side to the night side with extraordinary efficiency. Think of the planet as a single thermal system rather than a collection of climate zones. The star heats the day hemisphere continuously. That heat does not stay localized. It rises into the upper atmosphere where winds carry it around the planet. By the time air circulates back to the night side, it has distributed warmth globally. The night side never cools significantly because it receives a constant influx of heat from the day side through atmospheric circulation. The ocean beneath contributes to this stability. Water has high heat capacity. It absorbs enormous amounts of energy with only modest temperature increases. Earth's oceans moderate climate by storing summer heat and releasing it during winter. K2-18b's ocean, if it extends globally and reaches depths of hundreds of kilometers, would have heat capacity dwarfing anything Earth can offer. Once warmed, it would maintain its temperature essentially forever. At 120 degrees Fahrenheit, the ocean would be uncomfortably hot by human standards, but it is well within the range where thermophilic bacteria thrive on Earth. Hot springs in Yellowstone support microbial communities at these temperatures. Deep-sea hydrothermal vents host organisms in water exceeding 100 degrees Celsius. Life does not require cold comfort. It requires consistency. The biochemistry of thermophiles differs subtly from organisms adapted to cooler environments. Their proteins are more tightly folded, resistant to unraveling in heat. Their membranes contain lipids with saturated fatty acids that remain solid and functional at higher temperatures. Their DNA repair mechanisms work over time, fixing thermal damage before it accumulates. These adaptations carry costs in terms of metabolic complexity, but they work. Life finds ways. On K2-18b, organisms would not need heat tolerance adaptations. They would simply evolve in warmth from the beginning. Their biochemistry would be optimized for 120 degrees, the same way Earth life is optimized for the temperatures where it evolved. What seems extreme to us would be normal there, the baseline, the only temperature chemistry has ever known. This constant temperature has profound implications for evolution. On Earth, organisms must generalize. They must survive temperature ranges that span their environment. A fish in temperate waters experiences seasonal temperature changes that require physiological flexibility. Energy goes into maintaining that flexibility rather than specializing for a single optimal condition. But on K2-18b, life could specialize completely. Every biochemical pathway could be tuned for precisely 120 degrees Fahrenheit. No compromises, no backup systems for temperature variation, just pure optimization. The result would be metabolic efficiency. Earth life cannot match. Enzymes catalyzing reactions at exactly their optimal temperature. Membranes maintaining perfect fluidity without need for adjustment. Energy that on Earth goes into temperature regulation could on K2-18b go into growth, reproduction, complexity. Water itself behaves differently at 120 degrees. It remains liquid but closer to its boiling point at Earth's atmospheric pressure. On K2-18b, the thick atmosphere creates much higher surface pressure. Water's boiling point rises with pressure. At K2-18b's surface pressure, water would remain comfortably liquid even at 120 degrees, with no risk of boiling away. The phase diagram shifts, allowing water to exist as a stable liquid across a much wider temperature range than on Earth. This means the ocean could support an enormous diversity of chemical environments based on pressure and depth rather than temperature. Temperature remains constant throughout, but pressure increases with depth, changing how molecules interact, which reactions are favoured, which structures are stable. Life could stratify by pressure preference rather than temperature tolerance. Different species at different depths, each optimized for their particular pressure regime, all living at the same comfortable warmth. The atmospheric temperature also stays steady. Unlike Earth, where the troposphere cools with altitude, K2-18b's thick hydrogen envelope maintains warmth throughout its depth. This creates unusual convection patterns. On Earth, warm air rises, cools and sinks, driving weather. On K2-18b, the reduced temperature gradient means convection is driven more by humidity differences and chemical composition than by thermal stratification alone. Clouds on K2-18b, if they exist, would form from water condensing out of the hydrogen atmosphere. These would not be the fluffy cumulus clouds of Earth's skies. They would be dense, persistent layers where water vapor reaches saturation. Models suggest K2-18b might have a global cloud deck at a particular altitude where temperature and pressure favour condensation. Above the clouds, hydrogen-dominated air. Below them, a mixture of hydrogen and water vapour gradually increasing in water content until reaching the ocean's surface. Light filtering through these clouds would be dim and diffuse. No sharp shadows, no direct sunlight, just a general glow from above, reddish from the star's spectrum scattered by water droplets. The environment would feel subaqueous even in the atmosphere, a perpetual twilight where visibility extends for kilometers, but nothing ever appears sharply defined. In such conditions, photosynthesis as we know it would struggle. Plants on Earth require intense direct light to power their biochemistry, but chemosynthesis does not depend on light at all. Organisms could extract energy from chemical gradients, from the reaction of hydrogen with other compounds, from the slow dissolution of minerals into the ocean. The steady temperature ensures these chemical reactions proceed at constant rates, providing reliable energy sources that never fluctuate. The dimethyl sulfide detected in K2-18b's atmosphere hints at such chemosynthetic processes. On Earth, the molecules that produce DMS thrive at boundaries between different chemical environments, where oxygen meets anoxic water, where sulfur compounds from deep sources encounter organisms that can metabolize them. K2-18b offers similar boundaries, where the hydrogen atmosphere dissolves into water, where the warm ocean contacts cooler material from depth, where dissolved gases from the interior meet downwelling currents from above. At each boundary, chemical disequilibrium provides energy. Life, wherever it exists, consumes disequilibrium. It feeds on the flow from high energy to low, capturing some of that flow to power its own organization. K2-18b maintains numerous such flows, all steady, all persistent, all driven by the relentless input of stellar energy and the planet's own internal heat. The temperature is not too hot, not too cold, but more importantly, it is not variable. It is the Goldilocks condition not because it matches Earth, but because it is perfect for itself, perfect for chemistry that has had billions of years to adapt to precisely these conditions, perfect for biology that never had to learn temperature survival, only temperature optimization. Earth life is resilient because it must be. K2-18b life, if it exists, might be fragile in terms of temperature range, but exquisitely sophisticated in every other respect. Like a thoroughbred horse bred for one perfect track, rather than a Mustang bred to survive anywhere. Specialization enabled by stability, complexity enabled by constancy. Dimethyl sulfide is not a famous molecule. Most people have never heard its name. Yet everyone has encountered it. It is the scent of the sea, the slightly sulphurous smell that drifts from ocean waves breaking on shore. That odour comes from a molecule containing one sulphur atom bonded to two methyl groups. Simple in structure, profound in implication. On Earth, this molecule has a single dominant source: life. Specifically, marine microorganisms. Phytoplankton floating in the surface ocean produce a compound called dimethyl sulfoniopropanate, abbreviated DMSP. They use it to regulate osmotic pressure, balancing the salt concentration inside their cells with the seawater outside. When these organisms die or are consumed by other microbes, enzymes break down DMSP, releasing dimethyl sulfide as a byproduct. The DMS escapes into the atmosphere. Once airborne, it survives for only hours before photochemical reactions tear it apart. Ultraviolet light from the sun breaks the bonds holding the molecule together. Hydroxyl radicals scavenge it. Within a day, most of the dimethyl sulfide released from the ocean has been destroyed. The only reason Earth's atmosphere contains any DMS at all is that phytoplankton continuously produce it. Billions of tons annually. A molecular exhale from the living ocean. No known geological process creates dimethyl sulfide. Volcanoes emit hydrogen sulfide, sulfur dioxide, various sulfur compounds, but not DMS. Lightning can form some sulfur-containing molecules through atmospheric chemistry, but not DMS in significant quantities. Chemical reactions in anoxic sediments produce methane and other gases, but not DMS. Every attempt to identify an abiotic pathway to dimethyl sulfide on Earth has failed. This makes DMS what astrobiologists call a biosignature, a molecule whose presence in a planetary atmosphere points strongly toward biological activity. Not conclusive proof. Nothing in science is ever conclusive, but strong evidence. Evidence that shifts the burden of explanation. If you detect a methyl sulfide on a distant world, the default hypothesis becomes biology unless something else can explain it. K2-18b has dimethyl sulfide. The spectral signature is clear in multiple independent observations. The concentration exceeds 10 parts per million by volume. Compare this to Earth, where DMS measures below 1 part per billion. K2-18b's atmosphere contains dimethyl sulfide at levels roughly 10,000 times higher than our planet. This is not a subtle trace. This is abundant, persistent presence. The abundance matters because it relates to production rate. DMS breaks down quickly anywhere it exists. On K2-18b, with an atmosphere full of hydrogen and methane, chemical reactions would destroy DMS even faster than on Earth. Hydrogen is highly reactive. It strips electrons from other molecules. Methane can participate in photochemical chains that consume sulfur compounds. For DMS to reach 10 parts per million concentration, something must be producing it at prodigious rates, constantly, without pause. Calculate the replacement rate. If atmospheric chemistry destroys DMS with a half-life of days or weeks, then maintaining 10 parts per million requires generating tens of thousands of tons per day. Planetary scale production. Not a small isolated source like a volcanic vent or a localized chemical deposit. Something global, something systematic, something that operates across the entire surface or throughout the ocean. On Earth, only the biosphere operates at such scales. Only life, distributed across millions of square kilometers of ocean surface, produces molecules in quantities sufficient to affect atmospheric composition. Individual organisms are tiny, but billions of them, all metabolizing, all exhaling waste products, all participating in biogeochemical cycles, add up to planetary influence. The detection of dimethyl disulfide alongside DMS strengthens the biological interpretation. DMDS is another sulfur-containing organic molecule, closely related to DMS. On Earth, it also originates from biological processes, though it is less common and less studied than DMS. The presence of both molecules together suggests a sulfur cycle. Organisms producing sulfur-containing compounds, those compounds being modified chemically or biologically into related forms. The whole system creating a suite of molecules that collectively point toward metabolic activity. Alternative explanations have been proposed. Could unknown photochemistry in a hydrogen-rich atmosphere produce DMS without life? Laboratory experiments have explored this question. Researchers exposed mixtures of hydrogen, methane, hydrogen sulfide and other compounds to ultraviolet light, trying to synthesize DMS through purely chemical reactions. Some experiments succeeded in creating trace amounts of DMS, but they required hydrogen sulfide concentrations much higher than Webb detected on K2-18b. They also required low carbon dioxide levels, contradicting the abundant CO2 the telescope observed. Every abiotic pathway investigated so far requires conditions inconsistent with K2-18b's observed atmospheric composition. This does not prove such pathways are impossible. Science cannot prove a negative, but it shifts the probability. If life can easily explain the observations while abiotic chemistry requires special pleading and undetected ingredients, then life becomes the simpler hypothesis. The molecule also tells us something about the biochemistry involved. If organisms on K2-18b produce DMS through pathways similar to Earth's phytoplankton, then they likely use sulfur in their metabolism. Sulfur is abundant in the universe. It forms readily in stellar nucleosynthesis. Rocky planets and their oceans contain dissolved sulfates. Organisms that can metabolize sulfur compounds have a reliable energy source. On Earth, sulfur metabolism predates oxygen-based respiration. Ancient bacteria living in the anoxic oceans used sulfate as an electron acceptor, much like modern organisms use oxygen. These sulfur-reducing bacteria still exist today, thriving in environments without oxygen. Deep ocean sediments, salt marsh muds, anoxic lake bottoms. They represent an ancient biochemical pathway, one that might be more universal than oxygen-based life. K2-18b has no oxygen in its atmosphere. None detected, none expected in a hydrogen-dominated environment. Any life there would need alternative metabolic strategies. Sulfur metabolism provides exactly such an alternative. Organisms could oxidize or reduce sulfur compounds, extracting energy from the electron transfer. DMS might be a waste product of these reactions, an unintended byproduct that escapes into the atmosphere just as it does on Earth. The beauty of this interpretation is its simplicity. It does not require exotic biochemistry or chemistry unknown to science. It requires only that the universal laws of thermodynamics apply on K2-18b the same way they apply here. That chemical gradients provide free energy. That life evolves to exploit those gradients. That metabolism produces waste. That waste accumulates in the atmosphere when produced faster than chemical destruction can remove it. Every piece fits. The thick hydrogen atmosphere provides reducing conditions favouring sulfur chemistry. The warm ocean dissolves sulfates from the interior. The steady temperature allows metabolic optimization. The stable star provides endless time for evolution to refine these processes. And the dimethyl sulfide in the air provides a window through which we can see the result of all these factors working together. Yet uncertainty remains. The detection stands at 3 sigma confidence, 99.7% certain. In most fields, this would be conclusive. In astronomy, where careers and reputations hinge on claims about alien life, researchers demand more. 5 sigma, 99.9997%. The threshold where doubt becomes almost impossible to justify. Additional observations will either push the detection across that threshold, or reveal that the signal is not what it appears. Perhaps instrumental artifacts, perhaps contamination from some unexpected source. Perhaps the spectral features attributed to DMS actually arise from a different molecule entirely, one that absorbs light at similar wavelengths, but originates from geology or atmospheric chemistry. But for now, the data says dimethyl sulfide, the same molecule that Earth life produces, present at concentrations requiring continuous global production, in an atmosphere that provides no obvious abiotic pathway for its synthesis, on a planet that otherwise looks surprisingly habitable. The simplest explanation is that something on K2-18b is alive. Not intelligent, not technological, just alive in the basic sense. Metabolizing, reproducing, evolving, processing energy and matter in ways that create order from chaos. The same fundamental process that began on Earth 4 billion years ago and has continued unbroken to the present. That process exhales molecules. On Earth, we breathe the exhaust of ancient cyanobacteria that filled our atmosphere with oxygen. On K2-18b, if the data holds, we're detecting the exhaust of organisms that fill their atmosphere with sulfur. The molecule is small, simple, but what it represents is vast. The possibility that chemistry everywhere, given the right conditions, organizes itself into life. That the universe is not barren but fertile. That Earth is not unique but typical. That consciousness, should it arise anywhere, will look up at stars knowing it is not alone in looking. Numbers can deceive. A percentage feels concrete, solid, trustworthy. 99.7% certain sounds like near absolute knowledge. But in science, certainty is not a binary state. It is a spectrum, a probability distribution, a statement about how many times out of 1,000 you would expect to be wrong. 3 sigma. The phrase appears throughout the scientific literature. It is shorthand for a specific level of statistical significance, one that corresponds to a probability of 0.3% that an observed signal arose purely from random chance. Flip a coin 1,000 times. Getting 997 heads and 3 tails would be a 3 sigma deviation from the expected 50-50 split. Possible, but unlikely enough to make you suspect the coin is weighted. In particle physics, 3 sigma marks the threshold where researchers take a signal seriously enough to publish preliminary results. It means something interesting might be happening, something worth investigating further. But it is not yet a discovery, not yet proof. That requires 5 sigma, a probability of less than 1 in 3.5 million that chance alone produced the result. 5 sigma is the gold standard, the level where the scientific community collectively agrees that doubt is no longer reasonable. The detection of dimethyl sulfide on K2-18b stands at 3 sigma. This places it in interesting territory, strong enough to be compelling, not strong enough to be definitive. The measurement says that if DMS is not actually present in the planet's atmosphere, if the spectral features arise from some combination of noise, instrumental effects, or misidentified molecules, then the telescope would need to be extraordinarily unlucky to produce data that looks this convincing. But telescopes can be unlucky. Data contains noise. Random fluctuations can align in ways that mimic real signals. Instrumental artifacts can masquerade as molecular absorption features. Alternative molecules can absorb light at similar wavelengths, creating confusion about what is actually being detected. 3 sigma means these alternatives are unlikely, not impossible. Consider the challenge astronomers face. They are measuring variations in light intensity of perhaps 1 part in 10,000 at a distance of 124 light years. The light has travelled through space for over a century, potentially scattered or absorbed by interstellar dust. It arrives at Webb's mirrors carrying information encoded in wavelengths measured to nanometer precision. The detectors convert photons to electrical signals, which are digitized, transmitted to Earth, and processed through complex algorithms. At every step, errors can enter. Electronic noise in the detectors, thermal fluctuations despite the extreme cooling, cosmic rays striking the instrument, creating false signals, systematic biases in how the telescope tracks the star during transit, uncertainties in the calibration that converts raw detector counts into physical measurements of light intensity. Each source of error is small, but they compound. They create a background of uncertainty against which the real signal must be distinguished. Statistical analysis attempts to quantify this uncertainty. Astronomers measure the spectral data multiple times during different transits. They compare results from different instruments observing at different wavelengths. They run the data through independent analysis pipelines developed by separate research groups. If the signal is real, it should appear consistently across all these tests. If it is noise or artifact, it should vary randomly or disappear entirely under certain analysis choices. The dimethyl sulfide signal has survived these tests so far. It appears in nearest data. It appears in near-spec data. It appears in MIRI data. Different instruments, different wavelengths, same molecule. The consistency argues for reality, but consistency alone does not guarantee correctness. Systematic errors, problems affecting all instruments similarly, could produce consistent but incorrect results. This is why independent reanalysis matters. After Madhusudhan's team published their detection, other research groups obtained the same raw data and performed their own analysis. Some confirmed the signal, others questioned it. A NASA-led study in 2025 applied different modelling assumptions and found the DMS detection less convincing, suggesting alternative molecules like propine might explain the observations equally well. This back and forth is science functioning as designed. Claims are made, evidence is presented. Other researchers scrutinise the methodology, test alternative explanations, attempt to replicate the results. Gradually, through this adversarial collaboration, the truth emerges. Or at least the current best approximation of truth, always subject to revision as new data arrives. The 3 sigma threshold exists because scientists have learned from past mistakes. History contains numerous examples of preliminary detections that later evaporated, claim discoveries that turned out to be instrumental artifacts or misinterpretations. The 2020 announcement of phosphine in Venus's atmosphere seemed to point toward life in the clouds. Later analysis showed the detection was less certain than initially reported, possibly explained by other sulfur compounds or errors in data processing. The 1996 announcement of possible fossilized bacteria in a Martian meteorite generated enormous excitement. Closer examination revealed that the features attributed to microfossils could also form through non-biological processes. The magnetite crystals, the organic molecules, even the shapes that resembled bacterial cells, all had potential abiotic explanations. The claim did not survive scrutiny. These examples teach caution. They demonstrate why 5 sigma exists as a standard. They show that even 3 sigma, with its 99.7% confidence, leaves room for error. Science is not about achieving absolute certainty. It is about honestly acknowledging the level of certainty you have and remaining open to being wrong. For K2-18b, reaching 5 sigma requires more observation time. Webb's schedule is competitive. Every research team wants time on the most powerful telescope ever built. The request for 16 to 24 additional hours of observations must compete with proposals to study early galaxies, black hole mergers, supernova remnants, other exoplanet atmospheres. The allocation committee weighs scientific merit against available resources. Assuming the additional observations are granted and completed, 2 outcomes are possible. Either the signal strengthens, pushing past 5 sigma and cementing the detection of dimethyl sulfide, or the signal weakens, revealing that the initial detection was statistical fluctuation or misidentification. Both outcomes advance knowledge. Confirmation would mark the first credible detection of a biosignature on an exoplanet. Falsification would teach researchers what spectral features can be confused with biosignatures, improving methodology for future searches, What 3 sigma does provide, even without 5 sigma confirmation, is sufficient justification for taking the results seriously. It means the detection is not obviously wrong. It survives basic sanity checks. It warrants follow-up investigation. In a field where most potential biosignatures turn out to be false alarms, reaching 3 sigma represents meaningful progress. The number also contextualizes the claim properly. Madhusudan and his colleagues have not announced the discovery of alien life. They have announced the detection of a molecule at a confidence level that suggests life is a plausible explanation, but not yet the only explanation. The distinction matters. It prevents overhyping preliminary results, while acknowledging that those results are significant enough to discuss publicly. 3 sigma means we are watching a scientific process unfold in real time. A hypothesis has been proposed. Evidence has been gathered. The evidence is suggestive but not yet conclusive. More data is needed. The hypothesis will either strengthen into accepted fact or weaken into rejected speculation. Either way, we learn. This is how science progresses at the frontier. Not through sudden revelations of unquestionable truth, but through incremental increases in confidence, through measurements refined by repetition, through independent groups checking each other's work, through honest acknowledgement of uncertainty even while presenting the strongest case possible for what the data seems to show. 99.7% is not proof, but it is not nothing. It is a statement that something interesting appears to be happening on K2-18b, something that matches theoretical predictions for how a living biosphere would affect an exoplanet atmosphere. Something consistent across multiple instruments and wavelengths. Something worth investigating further with the best tools humanity can deploy. The universe does not care about our statistical thresholds. DMS either exists in K2-18b's atmosphere or it does not. Life either metabolizes there or it does not. The reality is fixed. What changes is our knowledge of that reality, advancing from ignorance toward understanding through measurements that gradually narrow the range of plausible interpretations. 3 sigma is far from ignorance, but it is also far from complete understanding. It is the middle ground where science lives, where evidence accumulates, where hypotheses face testing, where the universe slowly, grudgingly reveals its secrets to minds patient enough to ask questions carefully, and honest enough to admit when the answers remain uncertain. Beneath the clouds, beneath the thick hydrogen sky, lies an ocean that may stretch deeper than the distance from sea level to the cruising altitude of commercial aircraft on Earth. Hundreds of kilometers of water, perhaps more, an abyss so profound that pressure at the bottom would exceed anything Earth's oceans can produce by orders of magnitude. This is not water as we typically imagine it, not the clear blue liquid filling Earth's seas. The ocean of K2-18b exists in an exotic state, mixed with dissolved hydrogen from the atmosphere above. Hydrogen is soluble in water under pressure. On Earth, this solubility is minimal. Our atmosphere contains barely any hydrogen, and even if it did, surface pressure would not force significant amounts into solution. But K2-18b's atmosphere presses down with many times Earth's surface pressure, driving hydrogen into the ocean at concentrations unknown to terrestrial chemistry. Water mixed with hydrogen behaves strangely. It becomes less dense. Buoyancy changes. Objects that would sink in pure water might float in this hydrogen-enriched fluid. The mixture also becomes a powerful reducing agent, eager to donate electrons to other molecules. This creates a chemical environment fundamentally different from Earth's oxidizing oceans. where dissolved oxygen dominates reactivity. In Earth's oceans, organic chemistry centers on carbon-oxygen bonds. Organisms build carbohydrates, proteins with oxygen-containing groups, metabolic pathways that cycle through oxidized and reduced states using oxygen as the terminal electron acceptor. Remove oxygen, and those pathways fail. But introduce abundant hydrogen, and new pathways open. Hydrogenation reactions become favorable. Molecules can gain hydrogen atoms instead of losing them, running metabolic chemistry in reverse compared to familiar terrestrial biochemistry. The temperature of this ocean remains constant. At the surface, where it meets the atmosphere, roughly 120 degrees Fahrenheit. With depth, temperature might rise slightly due to heat from the planet's interior. But models suggest the gradient is gentle. Nothing like the dramatic temperature changes Earth's oceans experience between surface waters warmed by the sun and abyssal depths chilled to near freezing. Pressure increases relentlessly with depth. At 10 kilometers down, pressure would be 1,000 times Earth's surface atmosphere. At 100 kilometers, 100,000 times. Water under such pressure no longer behaves as ordinary liquid. It transitions through supercritical states where the distinction between liquid and gas blurs. Properties like density and viscosity change continuously, rather than jumping at a phase boundary. Strange ices form under these conditions, not cold ice, hot ice. Water crushed by pressure into crystalline structures that remain solid, despite temperatures that would boil water at Earth's surface. Ice of the Ice X, exotic phases with properties alien to everyday experience. These ices would sink, being denser than the liquid above, accumulating in a layer between the ocean and the rocky or metallic core beneath. Life could not exist in these extreme depths. No metabolism can function when pressure crushes molecules into configurations that destroy their chemical activity. But the upper ocean, the first 100 or perhaps several hundred kilometers, would be habitable. Pressure there, while intense by human standards, falls within the range that certain Earth organisms tolerate. Deep-sea bacteria live at the bottom of our deepest trenches, where pressure exceeds 1,000 atmospheres. Biochemistry survives. It simply adapts. What would such an ocean look like from inside? Visibility would be limited. The dissolved hydrogen and any suspended particles would scatter light. Color would shift toward red, the only wavelengths penetrating from the dim star above. Beyond a few hundred meters depth, darkness would be nearly complete. Not absolute, perhaps. Bioluminescence might provide faint illumination if life exists there. Chemical luminescence from reactions between dissolved compounds could create localized glows, but mostly darkness. Sound would travel differently. Water's density affects acoustic velocity. The hydrogen admixture changes properties further. Pressure gradients create layers where sound bends, creating acoustic channels that might carry vibrations for enormous distances horizontally. Organisms could potentially communicate across vast reaches of ocean, using low-frequency pulses that channel through these acoustic waveguides. The boundary between ocean and atmosphere would not be sharp. The thick atmosphere presses down with such force that the transition happens gradually. Surface tension barely exists under these conditions. Waves, if they form, would be sluggish and massive, driven by the atmosphere's slow circulation rather than by wind in the terrestrial sense. The surface would appear more like a boundary layer, a region where hydrogen-rich air gradually gives way to hydrogen-enriched water without a clearly defined interface. This creates unusual possibilities for life at the boundary. On Earth, The ocean surface is a distinct habitat. Plankton float there, harvesting sunlight. Neuston insects walk on the surface film. The boundary between air and water is sharp, stable, exploitable. On K2-18b, the boundary is thick and diffuse. Organisms might exist within this gradient region, neither fully aquatic nor aerial, but something in between, drifting in the dense lower atmosphere or the upper ocean depending on buoyancy adjustments. If dimethyl sulfide originates from biological activity, this boundary region seems a likely source. On Earth, DMS production peaks in surface waters where phytoplankton are most abundant. On K2-18b, the equivalent organisms would occupy the zone where the ocean meets the atmosphere, where dissolved gases are most concentrated, where chemistry is most active due to mixing between the two fluid layers. These organisms would not photosynthesize in the terrestrial sense. The light reaching them would be too dim, too redshifted. But chemosynthesis requires no light, only chemical gradients. The ocean atmosphere boundary provides ideal conditions: dissolved hydrogen from above, dissolved minerals from below, temperature steady, pressure moderate, a permanent interface where chemistry never stops flowing. Imagine microbial mats analogous to those on Earth, but adapted to hydrogen-rich conditions. Layers of organisms, each species occupying a niche defined by the chemical gradient it exploits. Some metabolizing hydrogen directly, oxidizing it using sulfur compounds as electron acceptors. Others feeding on the organic molecules these primary producers create. Still others decomposing dead material, recycling nutrients, completing the cycle. Such a system would be simpler than Earth's marine ecosystems. No fish, no whales, no complex food webs spanning multiple trophic levels, just microbes. But microbes can build impressive structures. Stromatolites on Earth, formed by bacterial colonies, create rock-like formations meters tall. On K2-18b, freed from the need to fight gravity as intensely in the buoyant hydrogen-water mixture, microbial colonies might form vast floating mats drifting with currents. These mats could be extensive enough to affect the planet's atmospheric chemistry. Billions of square kilometers of active biomass, all metabolizing sulfur, all producing dimethyl sulfide and related compounds as waste. The gases would bubble up from the mat, diffuse through the boundary layer and enter the atmosphere. From there, circulation patterns carry them around the planet, distributing the biosignature globally. Deeper in the ocean, below the productive surface layer, a rain of organic material would descend. Dead cells, fragments of larger structures, chemical compounds synthesized above and then released. This organic snow would support deeper ecosystems, organisms that survive by consuming what falls from above. On Earth, the deep ocean is fed by this rain. On K2-18b, the principle would be the same, but the details differ. Different molecules, different metabolic pathways, different organisms adapted to permanent darkness and crushing pressure. Near the bottom, where water meets the boundary with deeper high-pressure ices, chemical activity might pick up again. Heat from the interior creates gradients. Dissolved minerals percolate up from below. If K2-18b has a molten or partially molten interior, it might have the equivalent of hydrothermal vents. Cracks in the ice layer where superheated fluid rich in dissolved compounds erupts into the cooler ocean above. These vents would not vent water like Earth's black smokers. They might vent hydrogen-rich fluids carrying sulfur compounds, metals, and complex organics created through high-pressure chemistry in the planet's interior. Around these vents, ecosystems could thrive independent of the surface entirely. chemosynthetic communities powered by the thermal and chemical energy from below, rather than by anything happening in the atmosphere. The ocean is a reactor, multiple chemical systems operating simultaneously at different depths and temperatures, all connected by the slow circulation of fluid. Surface production creates organic molecules. Mid-depth decomposition breaks them down. Deep circulation brings nutrients back to the surface. The whole system cycles continuously, powered by the star above and the heat below, mediated by life that has inserted itself into every available niche. We cannot see this ocean directly. Webb's instruments detect only what happens in the atmosphere, but atmospheric chemistry reveals ocean chemistry. The gases we detect must originate somewhere. They do not spontaneously appear. They are produced by processes occurring at or below the surface. The atmosphere is a window into what lies beneath, a record written in molecules of what the ocean is doing. If the ocean teems with life, the atmosphere tells us so. If the ocean is barren, chemistry alone shapes atmospheric composition. The data from K2-18b suggests the former, not proves, suggests. The molecular ratios, the presence of compounds like DMS that require continuous production, the chemical disequilibrium that characterizes living systems on Earth, all point toward an ocean that is not just water, but a living fluid, filled with organisms too small to see individually, but vast in their collective impact. Chemistry seeks equilibrium. Left alone, reactions proceed until forward and reverse rates balance. Concentrations stabilize, change stops. A dead planet's atmosphere settles into this stillness. Molecules reach ratios determined purely by thermodynamics and temperature. Nothing disturbs the balance because nothing is consuming or producing gases faster than chemical kinetics allows. Earth's atmosphere is not in equilibrium. Oxygen comprises 21% of our air. Methane exists at parts per million. These gases should not coexist. Methane and oxygen react with each other, forming carbon dioxide and water. Given time, they would eliminate each other from the atmosphere entirely, yet both persist. The reason is life. Plants and photosynthetic bacteria produce oxygen continuously. Methanogenic archaea and other microbes produce methane. Geological processes contribute some of each, but biological production dominates. Without life constantly replenishing these gases, Earth's atmosphere would drift toward equilibrium within a few million years. Oxygen would react away. Methane would disappear. Carbon dioxide and nitrogen would dominate, with atmospheric composition resembling Mars or Venus. The persistence of chemical disequilibrium is a signature of active processes. When you find gases coexisting that thermodynamics says should react, something is maintaining that coexistence. Something is pumping energy into the system, driving it away from equilibrium. On Earth, that something is the biosphere. K2-18b's atmosphere shows disequilibrium. Methane and carbon dioxide coexist in roughly equal concentrations, each around 1%. In a hydrogen-dominated atmosphere, this combination is unusual. Hydrogen would prefer to react with carbon dioxide, reducing it to methane and water. Given sufficient time and temperature, CO2 should be consumed, leaving methane as the dominant carbon-bearing gas. But both gases persist at similar levels. Either the atmosphere is not in chemical equilibrium, or some process continuously produces carbon dioxide as fast as reactions consume it. The detection of dimethyl sulfide strengthens the case for disequilibrium. DML breaks down rapidly through photochemical reactions. Its presence at high concentrations means something is making it faster than chemistry can destroy it. Water vapor adds another layer of complexity. Models of K2-18b's atmosphere predict that water should condense into clouds at certain altitudes, forming a layer that shields the lower atmosphere from the star's ultraviolet radiation. Observations confirm water vapour, but show lower concentrations than expected, possibly because Webb's instruments primarily detect the dry upper atmosphere rather than the humid layers near the ocean surface. This vertical stratification matters for chemistry. In the upper atmosphere, ultraviolet photons drive reactions. Molecules absorb light and break apart, creating reactive fragments that recombine into new compounds. Lower in the atmosphere, shielded from UV by clouds and hazes, thermal reactions dominate. Molecules collide, exchange atoms, form and break bonds based on temperature and pressure rather than light energy. Life could exploit both regions. On Earth, some extremophiles thrive in stratospheric conditions, organisms that float in the upper atmosphere and tolerate intense radiation. Others live deep underground or underwater, isolated from any radiation. K2-18b could support stratified ecosystems where different organisms occupy different atmospheric layers, each adapted to the particular conditions of its altitude. The hydrogen that dominates K2-18b's atmosphere is itself interesting. Hydrogen is the simplest element, the most abundant in the universe, yet it is rare in Earth's atmosphere. Our planet's gravity cannot hold hydrogen long term. The gas is too light. Thermal motion gives hydrogen molecules enough speed to escape Earth's gravitational pull, so atmospheric hydrogen leaks away into space over geologic time. K2-18b has 8 times Earth's mass. Its gravity is stronger. Hydrogen escapes more slowly. Over the billions of years since the planet formed, it has retained much of its primordial hydrogen atmosphere. This creates a fundamentally different chemical environment than Earth's nitrogen-oxygen air. Hydrogen is a reducing agent. It donates electrons readily. In reactions with other compounds, hydrogen tends to add to molecules rather than strip from them. This makes K2-18b's atmosphere chemically active in ways opposite to Earth's oxidizing air. On Earth, iron rusts, organic compounds burn, reduced chemicals oxidize. On K2-18b, oxidized compounds might reduce, metals could remain in metallic form, chemistry runs in reverse. This has profound implications for metabolism. Life on Earth evolved in an oxidizing environment and uses oxygen as the final electron acceptor in respiration. Glucose is oxidized to carbon dioxide, releasing energy that organisms capture in ATP. Without oxygen, terrestrial aerobic life cannot function, but K2-18b offers an alternative. In a reducing atmosphere rich in hydrogen, organisms might run metabolism in reverse. Reduce carbon dioxide to organic molecules using hydrogen as an electron donor. Extract energy from hydrogenation rather than oxidation. Such metabolism exists on Earth. Hydrogen-atrophic methanogens consume hydrogen and carbon dioxide, producing methane. They thrive in anoxic environments where oxygen is absent. Hydrothermal vent ecosystems support themselves partly through hydrogen oxidation, using the hydrogen that vents from Earth's interior as fuel. These metabolic pathways are ancient, possibly predating oxygen-based respiration. On K2-18b, hydrogen-based metabolism would not be exotic or marginal. It would be the default, the primary way organisms extract energy from their environment. The abundance of atmospheric hydrogen means fuel is never limiting. Any organism capable of capturing that hydrogen and reacting it with other compounds has access to essentially infinite energy. Limited only by the availability of electron acceptors like sulfur or carbon dioxide, the methane detected in K2-18b's atmosphere could be a product of this hydrogen metabolism. Organisms consuming hydrogen and carbon dioxide, exhaling methane as waste. The process would simultaneously remove CO2 and produce CH4, explaining why both gases coexist at similar concentrations rather than one dominating completely. The atmosphere reaches a steady state where biological production balances chemical destruction for multiple gases simultaneously. This is the signature of a living atmosphere. Not equilibrium, but balance. Multiple competing processes operating at rates that maintain relatively stable concentrations. Production and destruction. Source and sink. Biology and chemistry locked in a dance where neither completely overwhelms the other. On Earth, atmospheric scientists can measure this balance precisely. Oxygen production from photosynthesis roughly equals oxygen consumption from respiration and oxidation. Methane production from wetlands and livestock roughly equals methane destruction in the atmosphere. When these rates fall out of balance, atmospheric composition changes. Rising carbon dioxide from fossil fuel combustion is exactly this kind of imbalance, production outpacing natural removal. K2-18b's atmosphere appears balanced. The gases detected are present at stable concentrations, neither increasing nor decreasing detectably over the time Webb has observed the planet. This stability suggests the processes producing and consuming gases have reached steady state. If biological activity contributes to this balance, then life on K2-18b is not emerging or dying out but established and persistent. The sulfur chemistry provides another window into this balance. Dimethyl sulfide oxidizes readily in any atmosphere. On Earth, hydroxyl radicals attack DMS, breaking it into sulfur dioxide and other fragments. These fragments can further oxidize into sulfate particles, which eventually rain out of the atmosphere. The whole cycle from DMS emission to sulfate removal takes days to weeks. K2-18b's atmosphere likely has similar chemistry. Hydrogen might even accelerate DMS destruction by providing additional reactive pathways. For DMS to accumulate to 10 parts per million concentration, biological production must be occurring at rates vastly exceeding the destruction rate. This implies not just the presence of sulfur metabolizing organisms, but their abundance. A thriving biosphere, not a sparse, struggling ecosystem barely hanging on. The ratio of different sulfur compounds might eventually reveal even more about the biology. On Earth, phytoplankton produce not just DMS, but a suite of related organosulfur molecules. The ratios among these compounds depend on the species of organisms, their metabolic state, environmental conditions. If Webb can detect multiple sulfur gases and measure their relative abundances, those ratios could constrain what kinds of organisms might be responsible. Similarly, nitrogen chemistry could provide clues. Webb has not detected significant nitrogen compounds on K2-18b so far. Ammonia is notably absent or present at only trace levels. On a dead world with hydrogen and nitrogen available, ammonia should accumulate. Its absence suggests consumption, either through reactions with other gases or through biological uptake. Some Earth organisms use ammonia as a nitrogen source for synthesizing proteins and nucleic acids. K2-18b life might do the same, keeping atmospheric ammonia concentrations low through biological demand. Every molecule detected or absent tells part of the story. Every ratio constrained, every abundance measured. The atmosphere is not just a collection of gases but a record of processes. Chemistry writes in one language, biology writes in another. learning to distinguish between them, to read the signature of life in atmospheric composition, is one of astrobiology's central challenges. K2-18b's atmosphere speaks clearly enough that scientists are paying attention. The chemical disequilibrium is pronounced. The presence of biosignature molecules is supported by multiple independent observations. The planetary conditions appear compatible with life, but atmospheres can deceive. Unknown chemistry might mimic biology. Models might be incomplete. Measurements might contain subtle, systematic errors that accumulated during data processing. This is why confirmation matters, why additional observations are necessary, why the detection must reach 5 sigma before claiming discovery. The atmosphere looks alive. But looking alive and being alive are not the same. Chemistry is vast. Nature is creative. The universe contains phenomena we've not yet imagined. Caution is warranted even when excitement is justified. Time is evolution's most precious resource. Given enough time, chemistry explores every pathway. Complexity emerges not through design, but through exhaustive trial. Life on Earth required 4 billion years to progress from simple cells to complex organisms capable of building telescopes and wondering about their place in the cosmos. 4 billion years of mutations, selections, extinctions, radiations. 4 billion years of the universe patiently waiting while chemistry learned to think. K2-18 will burn for 10 trillion years, perhaps longer. Red dwarfs are so efficient in their fusion that they outlive every other stellar class by factors of 1,000 or more. Our sun will extinguish in 5 billion years, swelling into a red giant that incinerates the inner planets before collapsing into a white dwarf. K2-18 will still be shining, still providing steady warmth, still illuminating whatever orbits it with patient, unwavering light. This longevity transforms what evolution can accomplish. On Earth, life has already consumed most of the time available. The Sun has another 5 billion years of stable burning, but complex life arose only 600 million years ago. The window for developing intelligence, technology, civilization is narrow. We happen to exist during one of the brief intervals when our planet can support complex ecosystems. Around K2-18, there is no narrow window. If microbial life emerged on K2-18b within 1 billion years of the planet's formation, as it did on Earth, it has already had time comparable to Earth's entire biological history. And it has trillions of years ahead. Evolution there operates without deadline, without the pressure of impending stellar death, without the urgency that comes from knowing time is finite. What happens to evolution when time becomes effectively infinite? On Earth, evolution is shaped by catastrophe. Asteroid impacts, volcanic eruptions, ice ages, drastic climate shifts. Each extinction event winnows diversity, eliminating species that cannot adapt quickly enough. The survivors inherit an emptied world where ecological niches have opened. They radiate into those niches, evolving rapidly to fill the available roles. Then stability returns until the next catastrophe. This punctuated pattern produces certain characteristics. Adaptability becomes crucial. Species that can tolerate environmental variation survive. Specialists that require specific conditions go extinct. The fossil record shows this pattern repeatedly. Generalists persist through crises. Specialists flourish between crises but vanish when conditions change. K2-18b may never experience such crises. Its star does not vary significantly in output. Its thick atmosphere buffers against external disturbances. Its orbit remains stable. There are no seasons to drive adaptation to changing conditions, no ice ages to force migration or extinction, no asteroid impacts massive enough to penetrate the thick atmosphere and cause global devastation. Just continuity, steady warmth, unchanging chemistry. In such an environment, evolution would optimize rather than diversify. Without environmental variation to reward generalists, specialists would thrive. Each organism could tune its biochemistry precisely for the conditions it experiences. Temperature exactly 120 degrees Fahrenheit. Pressure exactly whatever depth it occupies. Chemical composition exactly the local mix of dissolved gases and minerals. No need for tolerance ranges, no need for flexibility. Just perfection within a narrow niche. Over time, this could produce organisms so exquisitely adapted that they seem designed. Not designed by intelligence, but by endless trial refined across billions of years. Every enzyme catalyzing reactions at optimal speed. Every membrane maintaining perfect permeability. Every metabolic pathway producing zero waste. All byproducts channeled into useful reactions. Efficiency approaching theoretical limits. Earth life is messy. Evolution cobbles together solutions from available materials. DNA contains junk sequences. Biochemical pathways include unnecessary steps inherited from ancient ancestors. Organisms carry genetic baggage from their evolutionary history. This messiness is evidence of evolution's opportunistic nature, building new solutions by modifying old ones rather than engineering optimal designs from scratch. K2-18b life, given sufficient time without disruption, might transcend this messiness. Mutations that improve efficiency would be selected over billions of years. Unnecessary genes would be lost. Biochemical pathways would streamline. The result would be organisms that appear impossibly elegant, every component optimized, every function serving a purpose. Or perhaps not. Perhaps complexity itself creates inefficiency that no amount of selection can eliminate. Perhaps there are fundamental constraints that prevent biology from approaching engineering ideals. The only way to know is to observe what actually exists on worlds where time has been unlimited. The timescale also affects what complexity can emerge. On Earth, multicellularity evolved roughly 2 billion years after life began. The transition from single cells to coordinated multicellular organisms required specific innovations: cell adhesion molecules, communication systems, differentiation programs allowing cells to specialize. These innovations did not appear quickly. They required time for the right genetic machinery to evolve through incremental steps. If similar constraints operate on K2-18b, then 2 billion years would not be enough for complex life to emerge. But 6 billion years might be. 10 billion years almost certainly would be. The red dwarf's longevity means there is time for even improbable transitions to occur. Time for cellular cooperation to develop. Time for organisms to grow large and complex. Time for nervous systems to evolve if selection favors information processing. We have no reason to expect K2-18b hosts complex life. The biosignature detected points toward microbial metabolism, organisms producing dimethyl sulfide as a byproduct of sulfur chemistry. This could be accomplished by single-celled organisms no more complex than Earth's bacteria. Complexity requires not just time but ecological pressure, competition, predation, environmental gradients that reward larger size or better information processing. K2-18b's stable ocean might not provide such pressures. Without tides driven by a moon, without upwelling driven by seasonal temperature changes, without the environmental heterogeneity that Earth's continents create, the ocean could be relatively uniform. A vast soup where microbes float, consuming whatever chemistry provides, reproducing when resources allow, dying when they do not. Simple, effective, persistent. But persistence over billions of years allows for unlikely events. On Earth, multicellularity evolved independently multiple times. Plants, animals, fungi, and various algae all invented coordinated multicellular organization through separate evolutionary paths. This suggests that given enough time and enough organisms, the transition becomes likely rather than improbable. K2-18b has time. If it has life at all, it has had that life for billions of years, countless generations, uncountable opportunities for rare beneficial mutations to arise and spread. The probability of any single mutation is tiny, but multiply that probability by trillions of organisms reproducing over billions of years, and rare events become certainties. The red dwarf's gift is patience. It does not demand quick results. It doesn't punish slow adaptation. It simply continues shining, day after day, year after year, eon after eon, while life on its planets explores every possibility that chemistry and physics allow. This is both hopeful and humbling. Hopeful because it suggests that wherever life begins, it has time to develop. No cosmic deadline forces premature extinction. No stellar evolution cuts short the experiment. Life can take its time, literally, evolving complexity only when and if circumstances favour it. Humbling because it suggests that even if K2-18b hosts life, that life might remain microbial forever. Complexity is not inevitable. It is not a goal toward which evolution aims. It is one possible outcome among many, arising only when specific conditions make complexity advantageous. K2-18b's stable ocean might be perfectly suited for microbial existence, but offer no advantage to becoming large, differentiated, or intelligent. Or perhaps something does exist there that we would recognize as complex. Perhaps the ocean hosts organisms that, given billions of years, have developed senses and mobility and behavior. Perhaps they communicate through chemical signals or pressure waves. Perhaps they build structures, cooperate, compete, think. We cannot know from atmospheric data alone. Webb sees molecules, not minds. What we can infer is that if minds exist anywhere around red dwarfs, they have had ample time to develop, and red dwarfs are common. 3/4 of all stars in the galaxy, most host planets. Many of those planets orbit in zones where conditions might support liquid water and stable chemistry. If even a small fraction harbour life, and if that life has had billions of years to evolve, then the galaxy might be far richer in living worlds than we ever suspected. K2-18b could be one of countless such worlds, not unique, but typical. A common outcome of stellar and planetary evolution played out across billions of stars and trillions of years. The dimethyl sulfide in its atmosphere would then be not a singular anomaly, but evidence of a pattern, a signature that we will eventually detect on dozens or hundreds of exoplanets orbiting red dwarfs throughout the local galaxy. Time will tell, both in the sense that future observations will confirm or refute the K2-18b biosignature, and in the sense that time itself, vast cosmological time, has already determined what exists there. The universe does not wait for our instruments to catch up. Whatever K2-18b is, whatever lives or does not live in its ocean, that reality was established long ago and will persist long after our species has vanished. The red dwarf shines, The planet orbits, the chemistry continues, time passes, and perhaps somewhere beneath those clouds life persists. Not waiting to be discovered, not existing for our benefit, just being, metabolizing, reproducing, evolving slowly or remaining static. Indifferent to our telescopes and our questions, alive in the only way that matters, continuing. Light does not move instantly. This fact, fundamental to physics, creates a peculiar relationship between distance and time. When we observe distant objects, we see them not as they are but as they were. The farther away something is, the further back in time we look. K2-18b lies 124 light-years from Earth. The photons that reached Webb's mirrors in 2023 left that planet in 1899. Think about what Earth was like then. The Wright brothers had not yet flown. Radio was a new invention, barely understood. Einstein had not published his theories of relativity. The structure of DNA was unknown. Computers did not exist. Humans numbered less than 2 billion. Most had never seen electric light. The idea of observing planets orbiting other stars would have seemed like fantasy, impossible even to serious scientists. Yet while Earth stood at the dawn of the 20th century, K2-18b was already exhaling dimethyl sulfide into its atmosphere. Organisms there, if they exist, were metabolizing sulfur, processing hydrogen, continuing cycles that may have been running for billions of years. The light-carrying evidence of their existence began its journey across space, travelling through the void at 186,000 miles per second. That light traversed interstellar space for over a century. It passed through clouds of dust and gas. It travelled through regions where other stars were being born, where planets were coalescing from protoplanetary disks, where the raw material of future worlds swirled in gravitational eddies. The photons remained unchanged, carrying their encoded information, waiting for instruments sensitive enough to decode what they knew. By the time those photons arrived at Webb's mirrors, K2-18b had continued changing. If life exists there, it has evolved. New species may have emerged. Old ones may have gone extinct. The atmospheric composition might have shifted as ecosystems expanded or contracted. Whatever we see in the data is history, a snapshot of how things were when the light departed, not how they are now. This temporal displacement creates a strange asymmetry. We observe K2-18b as it existed during Earth's Industrial Revolution, but K2-18b, if anything there is looking back at us, sees Earth as it was 124 years earlier. They would see Earth in 1777, the American Revolution, the height of the Enlightenment. No radio signals, no artificial lights bright enough to see from space, no evidence that Earth hosts technological civilization. Of course, there is no reason to think anything on K2-18b is looking at Earth. No evidence of technology or intelligence. The biosignature detected points toward microbial life at most. But the thought experiment reveals something about the nature of astronomical observation. We and they, if they exist, are perpetually out of sync, observing each other's past, never quite contemporaneous. This delay also means that confirmation of life will be complicated. Suppose additional Webb observations push the detection to 5 sigma. Suppose follow-up studies confirm that dimethyl sulfide is indeed present at the concentrations initially reported. We would then know with high confidence that K2-18b hosted life 124 years ago. But what about now? The planet could have changed. A catastrophe might have sterilized it. A shift in atmospheric circulation could have altered chemical cycles. The organisms producing DMS might have evolved different metabolisms that no longer release that particular molecule. Unlikely, perhaps, given the planet's apparent stability, but not impossible. To know what K2-18b is like today, we would need to wait 124 years and observe again. If the DMS signature remains, we could conclude with reasonable confidence that the biosphere persists. If it vanishes, we learn that something changed. But we still would not know what the planet is like right now, at the moment of observation. We would know what it was like 124 years before that observation. This is the nature of astronomy. We study history. Not ancient history like looking at distant galaxies whose light has travelled for billions of years. Recent history. Historical time measured in human lifespans rather than geological epochs, but history nonetheless. For K2-18b, this temporal displacement is minor compared to the age of the system. If the planet formed 5 billion years ago, as similar systems suggest, then 124 years represents a tiny fraction of its existence. 0.002%. For practical purposes, what we see is what exists now. The planet's chemistry, its climate, its hypothetical biosphere have not changed meaningfully in the time it took light to reach us, but the principle remains philosophically interesting. We can never observe the universe as it is, only as it was. The present moment is inaccessible to astronomy. We live in our present but observe everyone else's past. The farther we look, the deeper into history we see. This creates a peculiar kind of loneliness. We are temporarily isolated from everything beyond our immediate vicinity. The light reaching us from the sun is 8 minutes old. We see the sun as it was 8 minutes ago. If the sun suddenly vanished, we would not know for 8 minutes. During that time, we would continue experiencing daylight, seeing a star that no longer exists. K2-18b is isolated from us by 124 years. Messages sent by light take over a century to arrive. If we transmitted a powerful laser signal toward K2-18b today, it would not reach the planet until the year 2149. Any response would not return until 2273. 250 years for a round-trip conversation. This assumes anyone there has technology to receive and respond, which seems vanishingly unlikely. More realistically, the only communication between our worlds happens through passive observation. We detect the light K2-18b reflects and emits. They, if they are capable of observation, might detect light from Earth. But we are not exchanging information in any meaningful sense. We are merely noticing each other's existence across a gulf too wide for interaction. Yet there is something profound in that noticing. For all of human history until recently, we believed ourselves alone. Not just alone in the solar system, but possibly alone in the universe. Every mythology, every religion, every philosophical tradition emerged in a context where Earth was the only known world harboring life. That assumption shaped how we understood our significance and our place in the cosmos. K2-18b challenges that assumption not through direct contact but through inference. Through light that travelled for 124 years carrying evidence of chemistry that on Earth is exclusively biological. If confirmed, this evidence would not tell us we are part of a galactic community. It would tell us only that life exists somewhere else, continuing its metabolic processes indifferent to our observation. But that alone would transform philosophy. It would mean life is not unique to Earth. That chemistry on other worlds also organizes itself into self-replicating systems. That the laws of physics and chemistry lead toward biology not just once but repeatedly. That the universe contains multitudes of living worlds, most of which will never contact each other, but all of which participate in the same fundamental phenomenon of increasing complexity through evolution. The 124-year delay also emphasizes how recently humans gained the ability to make such detections. Webb launched in 2021. Exoplanet transit spectroscopy became possible only in the early 21st century. For all of history before that, we could not have known about K2-18b's atmosphere even if we'd wanted to. The technology did not exist. The physics was understood in principle but not implemented in practice. This means K2-18b has been producing its biosignature for billions of years while we had no way to detect it. The dimethyl sulfide has been there, accumulating in the atmosphere, carried by circulation patterns, participating in photochemical cycles. But only now, only in the last few years, have we developed instruments sensitive enough to notice. How many other biosignatures exist undetected? How many worlds are broadcasting their chemistry into space, waiting for observers with the right instruments? Webb can study dozens of exoplanet atmospheres, but not thousands. The galaxy contains hundreds of billions of planets. Most will never be observed. Most biosignatures, if they exist, will remain unknown. K2-18b happened to be among the first studied, not because it is unique, but because it transits its star from our perspective and sits close enough that Webb can collect sufficient photons during those transits. Lucky geometry, lucky proximity, lucky timing that human civilization developed the technology to observe during the brief window when the planet transits as seen from our current location in the galaxy. In another century, Earth will have moved in its orbit around the galactic center. The Sun and K2-18 will have shifted positions relative to each other. The geometry that allows us to see transits might no longer work. Future astronomers might need different techniques to study that world's atmosphere. Or they might study entirely different planets that happen to transit from Earth's new vantage point. The universe is full of time. Light travel time, evolutionary time, stellar lifetime, geological time. Human time measured in years and decades seems brief against these cosmic scales. Yet it is in human time that we make our observations, ask our questions, build our telescopes. We live in the present but study the past, hoping to learn something about the nature of life and our place among the stars. K2-18b as we see it is already history. But history can teach. The light that left that world 124 years ago carries lessons about chemistry, about planetary atmospheres, about what biosignatures look like when observed from across the void. Those lessons inform how we search for life on other worlds, how we interpret the data, how we distinguish biology from geology in spectroscopic observations. And perhaps, 124 years from now, observers will look at data collected today and understand things we missed. They will have better instruments, better theories, better context from having studied hundreds of exoplanet atmospheres instead of dozens. They will see in our data patterns we cannot yet recognize. They will know whether K2-18b truly hosts life, or whether we were seeing only shadows that mimicked biology. Time moves forward, light moves outward, observations accumulate, understanding grows, and somewhere, 124 light-years away, a planet orbits a red sun, completely unaware that tiny instruments in a distant solar system are analysing the light it emitted more than a century ago, searching for signs of kinship across the darkness. K2-18b is not special. This statement might seem strange after spending thousands of words exploring what makes the planet remarkable. But in the context of the galaxy, K2-18b represents a type rather than an exception. Its star is ordinary, its mass and composition are common, its orbit places it in the habitable zone. But habitable zones exist around billions of stars. If K2-18b hosts life, The implication is not that we found the one living world, but that we found one of many. Red dwarfs comprise 3/4 of all stars in the Milky Way, roughly 300 billion stars in our galaxy. 225 billion of them are red dwarfs. Each of those stars can host planets. Many do. Surveys using the transit method have revealed that small planets, between Earth and Neptune in size, are extremely common around red dwarfs. More common, in fact, than around Sun-like stars. Sub-Neptunes like K2-18b appear to be among the most abundant planet types in the galaxy. They form readily in protoplanetary disks. Their moderate mass allows them to retain hydrogen atmospheres while still possessing solid or liquid interiors. They orbit their stars at distances where stellar radiation creates neither scorching heat nor frozen desolation. They are, by cosmic standards, unremarkable. This ordinariness matters. If life requires exceptionally rare conditions, then even a galaxy with 400 billion stars might host only a handful of living worlds. But if life emerges on common planets, orbiting common stars under common conditions, then the number of living worlds could be staggering. Millions, billions, more than we could ever hope to study individually. K2-18b orbits at 0.14 astronomical units from its star, close by the standards of our solar system but typical for a planet in a red dwarf's habitable zone. The reduced stellar output means habitable orbits lie much closer than Earth's orbit around the Sun. This close proximity actually helps observation. Planets closer to their stars transit more frequently and block a larger fraction of stellar light. Both factors make them easier to detect and characterize. Other sub-Neptunes exist in habitable zones around red dwarfs. Dozens have been identified. Most have not been studied in the detail K2-18b has received, but there is no reason to think they are fundamentally different. Similar sizes, similar masses, similar atmospheric pressures and temperatures. If one can support life, others likely can as well. The question becomes not whether habitable worlds exist, but what fraction of them are actually inhabited. Astronomers call this the occurrence rate. If 1% of habitable zone sub-Neptunes around red dwarfs host life, and if there are 10 billion such planets in the galaxy, then 100 million living worlds exist within our cosmic neighbourhood. If 10% are inhabited, 1 billion. If 50%, 5 billion. We have no way to know which number is correct. K2-18b, if its biosignature holds up to scrutiny, would represent a sample size of 1. Not enough to calculate occurrence rates with any confidence, but it would establish that the rate is not 0, that life can exist on Hycean worlds, that hydrogen-rich atmospheres do not preclude biology, that red dwarf systems are worth searching. Finding a second example would change everything. 2 living worlds around red dwarfs would suggest a pattern. 3 would confirm it. By the time we had studied 10 or 20 such systems, statistical analysis could begin to constrain how common life really is. We could start answering the question that has haunted humanity since ancient times. Are we alone? The search is already underway. Webb's mission includes characterizing dozens of exoplanet atmospheres. JWST is not the only instrument. Ground-based telescopes like the Extremely Large Telescope, under construction in Chile, will have the resolution to study exoplanet atmospheres from Earth's surface. NASA's Nancy Grace Roman Space Telescope, launching later this decade, will discover thousands of new exoplanets and characterize the brightest ones. Future missions are being planned specifically for biosignature searches. The Habitable Worlds Observatory, a concept being developed by NASA, would focus exclusively on finding and studying potentially habitable planets. It would observe in wavelengths optimized for detecting biosignature gases. It would study hundreds of systems over its operational lifetime. Within decades, we may have enough data to determine whether Earth-like and Haitian life are rare or common. The diversity of potential habitats expands beyond Haitian worlds. Gas giant moons might host subsurface oceans. Rogue planets drifting between stars could maintain internal heat long enough for life to emerge. Super-Earths with thick atmospheres might support chemistries unlike anything Earth has produced. The universe offers more variety than our imaginations encompassed when we first began searching for life beyond Earth. This variety means biosignatures might take unfamiliar forms. On Earth, oxygen produced by photosynthesis dominates our atmosphere. But oxygen is a product of our specific evolutionary history. A world where life never evolved, oxygen-producing metabolism might never develop an oxygen-rich atmosphere. Yet it could still be alive, metabolizing through other pathways, producing different waste gases. Dimethyl sulfide is one such alternative biosignature. Methane is another. Ammonia, nitrous oxide, methyl chloride, isoprene, all have been proposed as potential signs of life under the right conditions. None are as definitive as oxygen. All require careful analysis to distinguish biological from geological sources, but together they offer multiple ways to recognize life, even when it does not resemble Earth biology. K2-18b may be the first Haitian world where we detect biosignatures. It will not be the last if the detection proves correct. Other teams are already analyzing data from similar planets. Some show intriguing chemical features, others appear barren. Over the next few years, a picture will emerge of how common these hydrogen-rich ocean worlds are and what fractions show signs of life. The implications extend beyond science. Discovering that life exists on multiple worlds around red dwarfs would reshape philosophical and theological frameworks. Religions would need to accommodate the reality of cosmic biology. Philosophers would need to rethink questions about humanity's significance. Science fiction would seem less fictional. The perspective that Earth is the only living world, a view held by most humans throughout history, would become untenable. But would it change daily life? For most people, probably not. K2-18b is too distant to visit, too far to communicate with. The life there, if it exists, is microbial, not intelligent, not technological, not capable of building societies or creating art or asking questions about its place in the universe. The discovery would be profound scientifically but abstract in practical terms, yet abstractions matter. They shape how we see ourselves and our world. The Copernican revolution, the realization that Earth is not the center of the universe, had no immediate practical implications. It did not change agriculture or medicine or daily survival, but it changed how humans understood their cosmic position. It undermined geocentric worldviews and opened space for new ways of thinking about nature and existence. Discovering life beyond Earth would be another such revolution. It would confirm that biology is not a terrestrial anomaly, but a cosmic phenomenon, that the processes leading from chemistry to life operate wherever conditions permit, that the universe is not empty but teeming with living systems at various stages of complexity. This knowledge would influence how we treat our own biosphere. If life is common, then Earth is not uniquely precious but one instance of a universal pattern. Some might see this as diminishing Earth's importance. Others might see it as evidence that life, being common, deserves protection wherever it arises. The philosophical implications would be debated for generations. It would also affect space exploration. If Hessian worlds commonly host life, then missions to study them would become priorities. Not just remote observation, but eventually probes, landers, sample return missions. The technical challenges would be immense, landing on a planet with no solid surface, operating instruments in crushing pressure, returning samples through thick atmosphere. But if life exists there, the scientific return would justify the cost. Closer to home, it would inform the search for life in our own solar system. Enceladus and Europa, moons of Saturn and Jupiter, have subsurface oceans. If Hessian worlds can host life, perhaps icy moons can as well. The chemistry would differ. The energy sources might be geothermal rather than stellar, but the principle remains: liquid water, chemical disequilibrium, time, the ingredients life needs. K2 18b stands as a test case, a planet we can study from afar using our most advanced instruments. If we can confirm life there through spectroscopic observation, then we can apply the same techniques to hundreds or thousands of other worlds. Each detection refines our understanding. Each false positive teaches us about misleading signals. Gradually we build a catalogue of living worlds, a census of biology across the galaxy. That catalogue would reveal patterns. Which types of stars host living planets most frequently? Which planetary characteristics correlate with biosignatures? Which atmospheric compositions prove incompatible with life? From those patterns we could extrapolate, not just to the Milky Way, but to the universe as a whole. Trillions of galaxies, each containing billions of stars, each star potentially hosting planets. The numbers become almost meaningless in their immensity. But they matter. They matter because they replace the question, are we alone? With the question, how common is life? And that second question has answers, not answers we know yet, but answers that exist in principle, waiting to be discovered through observation and analysis. K2 18b may provide the first piece of data toward calculating those answers. One world, one detection, one molecule in an atmosphere 124 light-years away. From such small beginnings, revolutions grow, not revolutions in technology or politics, but revolutions in understanding, in how we see ourselves and our place among the stars, in whether we are unique or typical, alone or companioned by countless other living worlds scattered through the cosmos. If K2-18b is alive, then probably others are too. And if others are alive, then the galaxy hums with metabolism, exhales biosignatures, hosts chemistry that has organized itself into biology in millions of locations we've not yet found. The search has only begun. The discoveries, if they come, will reshape everything. Webb is only the beginning. The telescope represents a breakthrough in capability, but it is not the final word in exoplanet observation. Already, astronomers are planning missions that will extend and refine what Webb has started. The next decade will bring instruments specifically designed to find and characterize habitable worlds, to search for biosignatures with greater sensitivity, to map the diversity of planetary atmospheres across the galaxy. The Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, is scheduled to launch in the late 2020s. Roman will carry a coronagraph capable of directly imaging planets around nearby stars. Unlike Webb, which observes planets indirectly through transit spectroscopy, Roman will see the planets themselves. Faint dots of light separated from their star's glare by sophisticated optical systems that block starlight while allowing planetary light to pass. Direct imaging offers advantages that transit spectroscopy cannot provide. It works for planets that do not happen to transit from our perspective. It allows observation at any time rather than requiring alignment during transits. It can study planetary surfaces and cloud patterns in addition to atmospheric composition. Roman will survey thousands of stars, discovering planets that Webb cannot detect, characterizing atmospheres that transit observations miss. But Roman alone cannot answer all questions. Its coronagraph works best for planets orbiting farther from their stars, where angular separation makes blocking starlight easier. For close-in planets like K2-18b, transit spectroscopy remains the superior method. Future missions will combine multiple techniques, using the strengths of each approach to build comprehensive understanding. The European Space Agency's Ariel mission, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, will launch in the early 2030s. Ariel focuses specifically on exoplanet atmospheres. It will study 1,000 planets, measuring their composition, temperature structure, and cloud properties. By observing so many worlds, Ariel will reveal patterns that single object studies cannot show. Which types of planets have which types of atmospheres? How stellar radiation affects atmospheric chemistry? Where biosignatures are most likely to appear, ground-based telescopes are also advancing. The extremely large telescope under construction in Chile will have a primary mirror 39 meters in diameter. The Giant Magellan Telescope, also in Chile, combines 7 mirrors to achieve equivalent collecting area. The 30-meter telescope, planned for Hawaii or the Canary Islands, will match them in capability. These ground-based giants will rival space telescopes in sensitivity, benefiting from enormous mirror sizes that launch constraints prevent for space missions. Adaptive optics allows these ground-based telescopes to overcome atmospheric distortion. Deformable mirrors adjust thousands of times per second, compensating for turbulence in Earth's atmosphere. The result is image quality approaching space telescope performance, but with much larger apertures collecting far more light. For bright target stars, these telescopes will characterize exoplanet atmospheres in exquisite detail. But the most ambitious concept is the Habitable Worlds Observatory. NASA has designated this mission as a priority for the 2030s or 2040s. HWO would be designed from the ground up to find and study potentially habitable planets. Its mirror, potentially 6 to 8 meters in diameter, would be equipped with a star shade, a separate spacecraft flying in formation with the telescope to block starlight mechanically. The star shade would position itself tens of thousands of kilometers from the telescope, precisely aligned between the telescope and the target star. Its specially shaped edge would create a shadow, allowing the telescope to detect planets far fainter than could otherwise be observed. With this system, HWO could study dozens of Earth-like rocky planets in habitable zones around Sun-like stars, searching for oxygen, water vapor, methane, and other biosignature gases. HWO would also observe Hycean worlds like K2-18b. It could measure atmospheric composition with far greater precision than Webb achieves. It could detect trace gases present at parts per billion, rather than parts per million. It could distinguish between different molecules with overlapping spectral features. It could measure seasonal variations, if any exist, watching how atmospheric composition changes over years or decades. These future missions will not merely replicate Webb's observations, they will expand them. Webb detects molecules by looking at planets during transit. Future instruments will map those molecules across the planet's surface. They will measure wind speeds by detecting Doppler shifts in spectral features. They will characterize cloud decks by analyzing how light reflects from different atmospheric layers. They will observe planets at multiple wavelengths simultaneously, from ultraviolet through infrared, capturing data Webb cannot access. The technology enabling these advances continues developing. Detector sensitivity improves, optical coatings become more efficient, computer processing grows more sophisticated. Each generation of instruments builds on lessons from predecessors, incorporating improvements that seemed impossible when earlier missions were designed. But instruments alone are insufficient. Interpreting the data requires theoretical work. Laboratory experiments recreate conditions on distant planets, testing how molecules behave under exotic temperatures and pressures. Computer models simulate atmospheric chemistry, predicting what biosignatures should look like and what false positives might occur. Interdisciplinary teams combining astronomy, chemistry, biology, and geology work together to understand what observations mean. The dimethyl sulfide detection on K2-8b has already sparked such laboratory work. Chemists are exposing mixtures of hydrogen, methane, and sulfur compounds to ultraviolet light, attempting to synthesize DMS through purely abiotic pathways. Some experiments succeed in creating trace amounts, others fail completely. The results guide interpretation of astronomical data, helping distinguish biological from geological sources. Future observations will test specific predictions. If DMS on K2-18b is biological, its concentration might vary with time as organisms respond to environmental changes. Seasonal cycles, if they exist despite tidal locking, could drive population fluctuations that show up as atmospheric variations. Long-term monitoring would reveal these patterns if present. The telescope time required is substantial. Each transit observation takes hours. Multiple transits improve signal quality but multiply the observing time needed. Webb's schedule is oversubscribed. Hundreds of research teams compete for limited observing slots. Dedicating enough time to monitor K2-18b repeatedly requires weighing its scientific value against other worthy projects. But if the biosignature proves real, the case for continued monitoring becomes compelling. Confirming that life exists on another world would be worth substantial resources. NASA and other space agencies would likely prioritize such observations, allocating time that would otherwise go to different projects. The potential scientific return justifies the investment. Meanwhile, the search expands to other planets. Every system Webb observes teaches us something about planetary atmospheres. Even null results have value. A planet that looks habitable but shows no biosignatures tells us about the frequency of abiogenesis. If most habitable worlds are barren, life must be rare. If most show chemical disequilibrium suggesting biology, life must be common. Over the next 20 years, we will accumulate data on hundreds of exoplanet atmospheres. Some will be hot Jupiters, gas giants orbiting close to their stars. Others will be rocky super-Earths. Still others will be sub-Neptunes like K2-18b. Each category reveals patterns, which planets retain atmospheres, how stellar radiation affects chemistry, where water vapor appears, where potential biosignatures hide. This data will feed into modelling efforts. Planetary scientists will refine theories of atmospheric evolution. Astrobiologists will better understand which environments support life. Chemists will identify new classes of biosignature molecules. The field will mature from early exploration towards systematic characterization. Public interest will play a role. The discovery of extraterrestrial life, even microbial life, would capture global attention. Funding for follow-up missions would face less resistance. International cooperation might increase as nations recognize the shared human interest in answering fundamental questions about life's place in the universe. Education would adapt. Astrobiology would shift from speculative field to observational science. Students would learn not just about Earth life, but about Haitian life, about hydrogen-based metabolism, about biosignatures in exotic atmospheres. Textbooks would include exoplanet examples alongside terrestrial ones. The next generation of scientists would grow up knowing that life exists beyond Earth, but challenges remain. False positives are possible, instruments can malfunction, analysis can contain errors. Even if multiple observations confirm DMS on K2-18b, some uncertainty will persist until we understand the chemistry better. Science advances through reducing uncertainty, not eliminating it. Each observation constrains possibilities without providing absolute proof. The ultimate confirmation might require more direct methods. In the far future, perhaps a probe could visit K2-18b, not landing, which seems impossible on a world with no surface, but orbiting, sampling the upper atmosphere, analysing composition in situ rather than through distant observation. Such a mission lies decades or centuries away given current technology, but it is not physically impossible, just difficult and expensive. For now, we work with what we have: telescopes, spectrographs, computers, minds capable of interpreting data and imagining what it means. These tools have already revealed more about exoplanets than previous generations dreamed possible. They will reveal more still. K2-18b will continue to be monitored. Other promising targets will be added to the list. Data will accumulate. Papers will be published. Conferences will debate interpretations. Gradually, through the messy, collaborative process of science, understanding will emerge. The next steps are clear. More observations of K2-18b to push the detection toward 5 Sigma. Searches for similar biosignatures on other Haitian worlds. Laboratory work to understand the chemistry. Theoretical modelling to predict what life in these environments should produce. And patience. Science does not move at the pace of headlines, but at the pace of careful measurement and analysis. Webb has opened a door. The first definitive look at what may be a living atmosphere on a planet orbiting another star. The missions that follow will step through that door, exploring what lies beyond, mapping the diversity of worlds and the distribution of life across the cosmos. We stand at the threshold. The journey has only begun. There will be a moment. Not today. Perhaps not for years. But eventually, if the data holds, if additional observations confirm what Webb has seen, if the statistical confidence crosses from suggestive to conclusive, there will be a moment when humanity collectively realizes we are not alone. It will not arrive with drama. No radio message decoded. No spacecraft landing on the White House lawn. Just a press conference. A scientific paper published in a peer-reviewed journal. A graph showing spectral features that, after exhaustive analysis, can only be explained by biological activity on a world orbiting another star. The dimethyl sulfide signature on K2-18b confirmed to 5 Sigma, or a similar biosignature detected on another planet, or multiple detections across several worlds, creating a pattern too consistent to dismiss. The news will spread through scientific communities first. Astronomers, astrobiologists, chemists, all the researchers who've been following the story will recognize what the confirmation means. Some will feel vindication, others will feel surprise. A few will remain skeptical, proposing alternative explanations even as evidence mounts. This is how science works. Consensus emerges gradually through weight of evidence, not through revelation. Then the media will amplify the discovery. Headlines will announce what scientists have known for weeks or months. Social media will explode with discussion, debate, celebration. Some will declare the finding the most important in human history. Others will point out that microbial life on a distant world changes nothing about daily existence. Both perspectives contain truth. Religious communities will grapple with the implications. Some traditions will adapt easily, seeing no conflict between their theology and extraterrestrial life. Others will struggle, needing to reconcile scripture written when Earth seemed to be all that existed with the universe containing multitudes of living worlds. New interpretations will emerge, new understandings of what creation means on cosmic scales. Philosophers will debate what consciousness means if life is common. If biology emerges wherever conditions permit, does that diminish the significance of human consciousness? Or does it suggest that consciousness itself might be a universal property of sufficiently complex systems, arising inevitably from evolution given enough time? Questions that have no definitive answers but invite endless exploration. Artists will respond. Paintings depicting alien oceans. Music inspired by the rhythm of cosmic metabolism. Literature imagining what life under a red sun might experience. Stories about contact that will never happen. About isolation bridged only by observation. About kinship across gulfs too vast for conversation. The creative impulse to understand and represent this new reality will produce works we cannot yet imagine. But for most people, the moment will pass quickly. K2-18b is too far away to affect mortgage payments or grocery shopping. The life there, if it exists, is microbial, not sentient, not building civilizations, not creating art or asking questions, just metabolizing. The knowledge that we share the universe with other living systems will be intellectually acknowledged, but practically irrelevant to survival concerns that dominate human attention. Yet something will shift, subtle, gradual, a change in perspective that accumulates over generations. Children born after the confirmation will grow up knowing that Earth is not the only living world. They will learn about terrestrial biology and Heikian biology in school. They will understand chemistry as something that happens everywhere, not just in laboratories. They will see themselves as participants in a universal phenomenon, rather than unique accidents. The environmental movement might gain strength. If life is common, then biospheres are precious, not because they are rare, but because they represent successful examples of chemistry organizing itself against entropy. Each living world is an experiment that succeeded where countless others failed. Destroying Earth's biosphere becomes not just a tragedy for humanity, but a cosmic loss, eliminating one of the universe's working models for how life operates. Or perhaps the opposite occurs. If life is common, then Earth matters less. Other worlds with other organisms will persist regardless of what happens here. The pressure to preserve our biosphere might diminish if we know alternatives exist. Humanity's choices about climate, biodiversity, ecological destruction might shift in unpredictable ways once we know life exists elsewhere. The truth is, we cannot know how the confirmation will change us. History suggests that major revelations reshape culture slowly and incompletely. The Copernican revolution took generations to fully integrate. The acceptance of evolution continues to face resistance centuries after Darwin. The confirmation of extraterrestrial life will likely follow similar patterns. Rapid initial excitement followed by gradual, uneven absorption into collective understanding. But something seems certain. The search will intensify. If one biosignature can be detected, others can too. Funding for exoplanet observation will increase. New instruments will be built. Hundreds of planets will be characterized. This census of living worlds will grow from 1 to 10 to 100. Each detection will be less shocking than the last. The extraordinary will become ordinary. We will learn how common life really is, not through theory or speculation, but through measurement. The occurrence rate for Hycean life around red dwarfs, the frequency of oxygen atmospheres on rocky planets, the distribution of biosignatures across different stellar types. These numbers will exist. They will be written in papers and cited in textbooks. They will answer questions humans have asked since consciousness emerged. And somewhere in that data, patterns will appear. Life may favour certain conditions, certain planetary masses, certain stellar ages. The patterns will reveal rules governing where biology arises and persists. Those rules might be simple or complex. They might match our expectations or surprise us completely. But they will exist, encoded in the observations waiting to be decoded. K2, 18b will remain important historically. The first confirmed detection of a biosignature on an exoplanet, assuming the confirmation holds. But it will become one entry in a catalogue. Future observers will study it as we study the first telescopic observations of Jupiter's moons or the first measurement of a star's distance, important as precedent, superseded by more detailed observations. Yet for us, living through this moment of discovery, K2-18b represents something more. It is the boundary between assumption and knowledge, between wondering if we're alone and knowing we are not, between imagining life on other worlds and detecting its chemical signature in the light those worlds emit. The planet itself is indifferent to our observation. The organisms there, if they exist, continue their metabolic cycles unaware that beings on another world have noticed their existence. They process sulfur compounds, release dimethyl sulfide, participate in biogeochemical cycles that have been running for billions of years. Nothing about their reality changes because we have detected them, but our reality changes. We cannot return to cosmic loneliness once we know it was illusion. We cannot unknow that life exists elsewhere. The universe has become more populated, more alive, more interesting. Not because anything changed out there, but because our understanding of what is out there has deepened. This is the gift science offers, not comfort, not simplicity, not easy answers to difficult questions, but truth, insofar as we can determine it through careful observation and honest analysis. The truth about K2-18b is still emerging. The data points toward life but does not yet prove it conclusively. More observations will either confirm or refute the initial detection. Either outcome advances knowledge. If confirmed, we learn that Hycean worlds can host life, that hydrogen-rich atmospheres are compatible with biology, that the search for life should focus as much on sub-Neptunes around red dwarfs as on Earth-like planets around Sun-like stars. The search strategy changes based on empirical evidence rather than assumption. If refuted, we learn what biosignature false positives look like. We become more cautious about interpreting spectral features. We develop better methods for distinguishing biological from geological signals. Future searches benefit from understanding where previous searches went wrong. Either way, we learn. This is why the uncertainty does not paralyze the field. Science accepts uncertainty as inherent to the process. We make claims at 3 sigma and work toward 5 sigma. We propose hypotheses and test them. We build models and compare them to observations. Through iteration, through refinement, through honest acknowledgement of limitations, understanding grows. Somewhere beneath crimson clouds an ocean breathes, Or perhaps it does not. Perhaps the dimethyl sulfide arises from chemistry we have not yet understood. Perhaps K2-18b is a dead world where gases accumulate through processes that mimic life without being alive. The universe will tell us which reality is correct if we listen carefully enough. But for now, in this moment of possibility, we can allow ourselves to imagine an ocean world, vast and deep, warm and stable, filled with microbes that have metabolized for billions of years, producing molecules that drift into the atmosphere and then into space, traveling as light toward distant observers who finally, after all the time that has passed since those photons began their journey, have instruments sensitive enough to detect them. And in detecting them, we have touched something that may be alive, not physically, not through contact or communication, but through observation, through the patient work of collecting photons, measuring wavelengths, calculating concentrations, building models, testing hypotheses, through the scientific method applied across 124 light-years of space. If life is there, it has always been there, but we have only just learned to see it, and in learning to see it, we have changed forever. We are not alone. The universe is not empty. Chemistry has become biology not just once, but twice, at minimum, and likely many more times than that. The implications will unfold over decades and centuries, but the moment, the threshold moment when we first realize these truths, belongs to now, to this discovery, to this planet, to K2-18b and its ocean that may, against all the loneliness we've felt staring up at the stars, be breathing still.